The last normal moment. Minutes 0 to 5. Imagine standing on a beach 66 million years ago, in what will one day be called the Yucatan Peninsula. The morning sun rises over a shallow, crystal-clear sea. The water is warm, almost bathwater temperature, teeming with ammonites spiraling through the currents, and massive mosasaurs patrolling the depths. The air smells of salt and vegetation, carried on gentle trade winds that have blown unchanged for millions of years. On the shore, a herd of hadrosaurs grazes peacefully on ferns and cycads. Their duck-billed mouths work methodically, grinding vegetation with hundreds of tiny teeth. Baby hadrosaurs stay close to their mothers, occasionally calling out with high-pitched chirps. In the forest beyond, a Tyrannosaurus rex rests in the shade of a giant sequoia, its massive head lowered, eyes half-closed in contentment after a recent kill. Pterosaurs with wingspans of 10 meters soar overhead, their shadows gliding across the landscape like silent ghosts. This is not the harsh, volcanic wasteland many imagine when they think of the dinosaur era. This is a world at its evolutionary peak. Dinosaurs have ruled Earth for 165 million years. They have survived multiple extinction events, adapted to every environment from polar forests to scorching deserts, and diversified into thousands of species. They are not primitive monsters waiting to die out. They are the most successful large animals in Earth's history. The climate is warmer than today, with no ice caps at either pole. Sea levels are higher, flooding continental interiors and creating vast, shallow seas rich with life. Flowering plants, a relatively recent innovation, have transformed the landscape with colors never seen before in Earth's history. Bees buzz between blossoms. Small mammals, no larger than rats, scurry through the underbrush. Birds, descendants of small feathered dinosaurs, sing in the trees. Everything is normal. Everything is as it has been for longer than humans can truly comprehend. The rhythms of life continue unchanged. Predators hunt. Prey animals flee or fight. Plants grow toward the sun, and the great cycles of birth and death turn endlessly. But 66 million years ago, on this particular morning, normal is about to end. High above Earth's atmosphere, something is approaching. It has been approaching for millions of years, falling through the void of space at 70,000 kilometers per hour. It is a mountain of rock and metal, roughly 12 kilometers in diameter, weighing more than 1 trillion tons. It is an asteroid, and its trajectory has been set by gravitational forces that began with the formation of the solar system itself. For the last few million years, this asteroid has been falling toward the Sun from the distant asteroid belt between Mars and Jupiter. Perhaps it was knocked from its stable orbit by a collision with another asteroid, or perhaps Jupiter's immense gravity slowly pulled it inward. Whatever the cause, it is now on an intercept course with Earth. The mathematics are inexorable. The physics are implacable. Nothing can stop what is about to happen. As it enters Earth's atmosphere, the asteroid is moving at 20 kilometers per second. That is more than 50 times faster than a rifle bullet. At this speed, the air itself cannot get out of the way fast enough. Instead, the atmosphere compresses in front of the asteroid, heating to temperatures hotter than the surface of the sun. The asteroid begins to glow, brighter than 1,000 nuclear weapons detonating simultaneously. For creatures with eyes to see, the sky suddenly ignites. A new sun appears, blazing with impossible brightness, growing larger by the second. It is so bright that it casts hard shadows even in full daylight. It is so bright that it can be seen from thousands of kilometers away. The hadrosaurs on the beach lift their heads. Their simple nervous systems register something wrong, something their instincts cannot process. The light is coming from the wrong direction. It is getting brighter. Some of them begin to call out in alarm. The Tyrannosaurus rex opens its eyes and rises to its feet, confused by this strange dawn coming from the south. The pterosaurs in the sky wheel in confusion, their navigational instincts overwhelmed by this impossible celestial object. They have 3 seconds to live. The asteroid strikes the shallow sea off the coast of what will one day be Mexico. It is traveling so fast that from the perspective of anything on the ground, it appears to simply materialize. One instant the sky is on fire. The next instant there is an impact. The asteroid does not slow down when it hits the water. At these speeds, water might as well be concrete, and concrete might as well be water. Both are simply matter to be displaced. The asteroid punches through 300 meters of seawater in less than a second, vaporizing billions of tons of ocean in an instant. The water does not splash. It does not have time to splash. It simply ceases to exist, converted to superheated plasma. Then the asteroid hits the bedrock. The impact releases energy equivalent to 10 billion Hiroshima bombs detonating simultaneously. To put that in perspective, all the nuclear weapons ever built by humanity, if detonated at once, would release approximately 1% of the energy of this impact. The largest volcanic eruption in recorded human history, Tambora in 1815, which caused the year without a summer, was 1/10,000th as powerful. This is energy on a planetary scale. The bedrock, which has sat undisturbed for hundreds of millions of years, offers no more resistance than tissue paper. The asteroid plows downward, creating a tunnel through solid rock, going deeper and deeper. It punches through limestone, then granite, then the deeper metamorphic rocks of Earth's crust. In the first half-second of impact, it burrows 25 kilometers into the planet, reaching depths where rock normally flows like taffy under the immense pressure of everything above it. Then physics catches up. The asteroid's kinetic energy, its energy of motion, must go somewhere. It cannot simply disappear. The laws of thermodynamics are absolute. All that energy converts instantly into heat, into pressure waves, into the violent reorganization of matter. The asteroid itself vaporizes. 1 trillion tons of rock and metal, compressed and flash-heated to temperatures exceeding 100,000 degrees Celsius, turns into an expanding ball of plasma. The rock it has displaced vaporizes too. Then the rock around that vaporizes. A spherical cavity of pure energy begins to expand outward from the impact site at speeds that defy human comprehension. This is the beginning. The hadrosaurs on the beach, standing perhaps 500 kilometers from impact, see the sky turn white. Every single thing in their line of sight toward the south vanishes behind a wall of light brighter than they can process. Their retinas burn instantly, but they do not have time to register blindness. The light is not just visible light. It is every wavelength: ultraviolet, X-rays, gamma rays, a full spectrum assault of electromagnetic radiation. Half a second after impact, the thermal pulse reaches them. Imagine opening an oven and feeling the wave of heat on your face. Now multiply that by 1 million. The air temperature goes from a comfortable 25 degrees Celsius to over 2,000 degrees in a fraction of a second. The hadrosaurs do not burn, they flash-ignite. Their bodies contain water, and water at these temperatures explosively converts to steam. Their skin, their muscle, their organs expand and rupture simultaneously. They are dead before their nervous systems can transmit the sensation of pain. The forest behind them ignites. Every tree, every fern, every living plant bursts into flame simultaneously. Animals in the undergrowth, insects in the bark, bacteria in the soil, all of it flash cooks. The Tyrannosaurus rex ignites like a torch. Pterosaurs in the air catch fire mid-flight and plummet to the ground as burning meteors. Everything within 1,500 kilometers of impact point dies in the first 5 seconds. Not most things. Not almost everything. Everything. 100% mortality. The thermal radiation alone is sufficient to kill every living creature larger than a bacterium. The world's most perfect predator, the culmination of 165 million years of evolution, dies in less time than it takes to blink. But this is just the beginning. The thermal pulse is merely the first wave of destruction, the fastest killer, the advance messenger of what is coming behind. Because behind the light, traveling slightly slower but infinitely more destructive, comes the pressure wave. At ground zero, the bedrock cannot withstand the forces being exerted upon it. Rock that has been solid for hundreds of millions of years behaves like a liquid, like a water droplet struck by a bullet. The impact site becomes a splash crater, but instead of water droplets, house-sized boulders are launched into space. Instead of ripples, mountain-high walls of shattered rock race outward in all directions. The pressure wave is not wind, it is not a storm. It is a wall of compressed air and shattered matter moving at supersonic speeds, carrying the force to reshape continents. Within the first minute after impact, this pressure wave has already traveled 100 kilometers in all directions. Everything in its path ceases to exist as recognizable matter. Rock shatters into sand. Sand compresses into new rock. Forests are not knocked down, they are erased. The ground itself ripples like the surface of a pond. For any creature that somehow survived the initial thermal pulse, death comes now in a different form. The pressure wave hits with force measured not in pounds per square inch, but in atmospheres of pressure. 50 atmospheres, 100 atmospheres, pressures that exist naturally only deep underwater or in the hearts of planets. Bodies compress, bones shatter, internal organs rupture. But again, death is instantaneous. These creatures have no time to suffer. The shallow sea at ground zero simply vanishes. The impact has vaporized a significant fraction of it, and what remains is blasted away in a tsunami that radiates outward in all directions. This is not a normal tsunami. Normal tsunamis, caused by earthquakes, involve the entire water column moving at speeds of 700 kilometers per hour. This tsunami is moving at the speed of sound, pushed by pressures that can move mountains. Within 5 minutes, waves 300 meters high are racing across the western interior seaway, the shallow sea that divides North America. Within 10 minutes, these waves will strike coastlines thousands of kilometers away, traveling kilometers inland, drowning everything that has survived the thermal pulse. But for creatures near ground zero, the tsunami is irrelevant. They are already dead. Everything within 2,000 kilometers is already dead. The sky is dark now, not from night, but from the billions of tons of vaporized rock and debris that have been launched into the atmosphere. The sun is completely obscured. The only light comes from the millions of fires that burn across the landscape and the continuing glow from ground zero, where rock itself is still liquid, still glowing white-hot. And still, this is just the beginning. The asteroid may have vaporized, but its matter and energy are very much present. Millions of tons of rock, heated to temperatures found in stellar cores, have been launched straight up. This material is moving so fast that it escapes Earth's atmosphere entirely. It arcs up into space, following ballistic trajectories, spreading out across the sky. What goes up must come down. And when this material comes down across the entire planet, the real nightmare will begin. 5 minutes have passed since impact. The age of dinosaurs has ended. The age of fire is just beginning. The sky rains fire, minutes 5 to 30. The debris cloud rising from the impact site is beyond anything in human experience. Imagine every volcanic eruption in recorded history happening simultaneously. Then multiply that by 1,000. The column of vaporized rock, superheated gas, and pulverized matter rises straight up like a spear thrust into heaven itself. It climbs 10 kilometers, 20 kilometers, 50 kilometers, punching through the stratosphere and continuing upward. At 100 kilometers altitude, the debris cloud reaches the edge of space. But it does not stop. The most energetic material, heated to plasma temperatures and moving at escape velocity, continues rising. Some of it will reach altitudes of 1,000 kilometers before gravity finally wins and pulls it back down. Some of it, the fastest moving particles, will escape Earth's gravity entirely and drift through the solar system forever. Tiny ambassadors of Earth's worst day. But most of the material follows a different trajectory. Millions upon millions of tons of rock, melted into spherical droplets by the heat of impact, arc through the upper atmosphere like bullets. These are called tektites, natural glass beads forged in the fires of catastrophe. Each one is still glowing hot. Each one is traveling at kilometers per second. And there are trillions of them, spreading across the sky like a malevolent swarm. The physics of what happens next is brutally simple. These particles have been launched on ballistic arcs that will bring them down all across the planet. They are falling back through the atmosphere at hypersonic speeds, and when objects move that fast through air, they compress the atmosphere in front of them. That compression generates heat. Tremendous, terrible heat. Within 15 minutes of impact, the first tektites begin to re-enter the atmosphere over North America. They are coming down in sheets, in clouds, in storms of molten glass. Each particle is small, perhaps the size of a grape or a marble, but each one is radiating heat like a tiny sun. And there are so many of them that the sky itself begins to glow. A triceratops in what will one day be Montana looks up at the darkening sky. It survived the initial impact by sheer distance, 3,000 kilometers from ground zero. The thermal pulse reached here too, but attenuated by distance and atmosphere, it was survivable. The animal suffered burns, its hide blistered and smoking, but it is still alive. It is confused, hurt, frightened by the darkness that has swallowed the sun, but it is alive. Then the sky above it turns orange. The tektites are hitting the upper atmosphere now, tens of thousands of them visible at once, each trailing a luminous tail of superheated air. They look like meteors, like shooting stars, but they are coming down everywhere, filling the sky from horizon to horizon. The Triceratops cannot understand what it is seeing. Nothing in its evolutionary history has prepared it for this. The temperature begins to rise. This is the critical moment, the mechanism of death that will prove far more devastating than the initial impact. Those tektites, billions upon billions of them, are radiating thermal energy as they fall. They are converting their kinetic energy, their speed, into heat through atmospheric friction. And that heat is radiating downward, toward Earth's surface. Imagine standing near a campfire and feeling the warmth on your face. Now imagine 1 million campfires in the sky above you, all radiating simultaneously. Then multiply that by 1,000. The thermal radiation from re-entering debris creates what scientists will later call an infrared pulse. The sky becomes an oven. The air itself becomes a weapon. Within 20 minutes of impact, the global temperature begins to spike. At first, it is subtle. The air temperature rises from 25 degrees Celsius to 30 degrees, then 40 degrees. Animals already stressed by the darkness and confusion begin to pant, seeking shade that no longer provides relief. The shade is just as hot as the sun because the heat is coming from everywhere, from the sky itself. 50 degrees Celsius, 60 degrees. The temperature climbs with terrifying speed. Small mammals in their burrows begin to dig deeper, instinctively seeking the cool earth. Birds try to flee, but there is nowhere to fly to. The entire sky is on fire. Flying creatures, already exhausted from the initial shock waves and thermal pulse, begin to fall from the sky as heat exhaustion overtakes them. Pterosaurs, some of the last of their kind, spiral down to Earth and do not rise again. 70 degrees Celsius, 80 degrees. The Triceratops is in agony now. Its massive body, designed to retain heat in cooler climates, has become a liability. It cannot cool itself fast enough. Its blood is overheating. Its brain is cooking inside its skull. It stumbles, falls to its knees, and does not get up. Around it, dozens of other animals are doing the same. Some are already dead, their nervous systems shut down by hyperthermia. Others are minutes away. 90 degrees Celsius, 100 degrees. Water begins to boil at 100 degrees Celsius. The moisture in plants begins to vaporize explosively. Trees that survived the initial thermal pulse because they were far from ground zero now face a different killer. The water in their cells turns to steam. The pressure builds inside their trunks, inside their branches, inside every leaf. Then they explode. Literally explode. The forests of Earth detonate like strings of firecrackers, the sound of splitting wood echoing across continents. And with the explosion of vegetation comes ignition. The air temperature is now above the flashpoint of organic matter. The fragments of exploding trees, the dried vegetation on the ground, the bodies of dead animals, all of it ignites simultaneously. Within minutes, forest fires erupt across entire continents. These are not normal wildfires that burn and spread gradually. These are firestorms, conflagrations that generate their own weather systems, create their own winds, feed themselves with hurricane-force convection currents. From space, if anyone could observe it, Earth's surface is transforming. The night side of the planet, which should be dark, is glowing. Thousands of individual fires merge into continental-scale infernos. The day side is even worse. The re-entering debris creates a light show more spectacular and more deadly than any aurora. The sky pulses with orange and red and yellow, waves of color that represent waves of death. In the oceans, creatures are dying by the billions. Marine reptiles, mosasaurs and plesiosaurs that have ruled the seas for millions of years, surface to breathe and find the air itself unbearable. The water temperature is rising too, heated from above by the burning sky. Fish swim deeper, seeking cooler water, but there is a limit to how deep they can go. Many species are adapted to specific temperature ranges, specific pressures. They cannot simply relocate to the abyss. Ammonites, those beautiful spiral-shelled cephalopods that have existed since before the dinosaurs, are particularly vulnerable. Their shells provide no protection against heat. They cannot burrow into the sea floor. They cannot escape. In their billions, they begin to die, their bodies sinking through darkening waters, beginning a slow rain of death that will continue for hours. On land, the situation is even more catastrophic. 25 minutes have passed since impact, and the global average temperature has risen by more than 50 degrees. In some regions, particularly those where the debris concentration is highest, the air temperature exceeds 150 degrees Celsius. This is hot enough to denature proteins, to break down the fundamental chemistry of life itself. Every land animal larger than a bread box is either dead or dying. The small exceptions are those that can burrow, that can get underground where the earth itself provides insulation. Mammals in their dens, reptiles in deep crevices, amphibians buried in mud at the bottom of ponds. These have a chance. But it is a slim chance, because the fires are spreading. The forest fires, now continental in scale, are generating their own feedback loops. The flames consume oxygen and release carbon dioxide and smoke. The smoke rises into the already darkened sky, making it darker still. The heat from the fires creates massive updrafts that pull in air from surrounding areas, creating winds of 100 kilometers per hour or more. These winds spread the fires even faster, casting embers kilometers ahead of the main blaze. A herd of Edmontosaurus, duck-billed hadrosaurs that have been running blindly through the darkness, finds their path blocked by a wall of flame. They try to turn, to run in another direction, but the fire is everywhere. It surrounds them, closes in on them, and they die screaming, their calls echoing across a dying world. In the skies above, the debris continues to fall. The tektites are joined now by larger fragments, some the size of houses, some the size of buildings. These impact the surface with tremendous force, creating secondary craters, generating new shock waves, adding to the chaos. Each impact kicks up more dust, more debris, more material that will eventually circle the globe and blot out the sun for months. The Western Interior Seaway, the shallow ocean that bisects North America, is experiencing its own apocalypse. The initial tsunami has passed, scouring the coastlines, drowning everything within kilometers of the shore. But the water that was pushed inland is now rushing back, creating a reverse tsunami. The seaway becomes a chaos of competing currents, whirlpools kilometers across, waves that clash and build to impossible heights. Marine life is tossed like toys in a bathtub. Massive mosasaurs, predators 12 meters long, are thrown onto newly formed beaches and left to die in the burning air. Smaller fish are simply torn apart by the violence of the water itself. The seabed is scoured clean. Every organism, every shell, every fragment of life swept away or buried under meters of displaced sediment. And still the debris falls. By 30 minutes after impact, the primary thermal pulse from re-entering debris is beginning to wane. Most of the material that was going to come down has come down. The sky is still dark, still filled with dust and smoke, but the terrible glowing has diminished. The air temperature, which peaked at levels incompatible with life, begins to slowly drop. But this is not a reprieve. This is not mercy. The fires are self-sustaining now. They no longer need the heat from the sky to feed them. They have fuel in abundance. The forests that covered continents, the grasslands that stretched from horizon to horizon, the bodies of billions of dead animals. They will burn for weeks, for months, consuming everything combustible and releasing millions of tons of carbon dioxide and toxic smoke into the atmosphere. The immediate global inferno is over. The firestorm from space has passed. But the age of fire has only just begun, and behind it, even worse horrors are gathering. 30 minutes have passed since the asteroid struck. Perhaps 10% of all species on Earth are already extinct. The death toll is measured not in millions, not in billions, but in numbers that have no meaning. Every individual animal, every single organism, represents billions of years of evolutionary history, millions of years of adaptation, thousands of generations of survival. All of that is being erased. And the worst is yet to come. The shock wave circles the globe. Minutes 30 to 90. The pressure wave from the impact is still traveling, still carrying devastation outward from ground zero, like ripples from a stone thrown into a pond. But these are not gentle ripples. This is a wall of compressed air and shattered matter moving at supersonic speeds, a hammer blow delivered by physics itself. At 30 minutes after impact, this shock wave has traveled roughly 3,000 kilometers from the impact site. It has crossed the entirety of North America, obliterating everything in its path. Mountains have been stripped of their forests. Valleys have been filled with debris. Rivers have been pushed from their beds. The landscape itself has been reorganized by forces that make hurricanes look gentle. But the shock wave is not weakening significantly. It is governed by the same physics that creates thunder from lightning, but magnified to planetary scale. The energy released by the impact is so immense that the atmosphere itself becomes a transmission medium for destruction. The wave propagates through air, through water, through solid rock, carrying its message of annihilation to every corner of the globe. In what will one day be Europe, a family group of Rhabdodon, small plant-eating dinosaurs, huddles together in a shallow cave. They survived the thermal pulse from re-entering debris because they were underground when it happened, sheltering from the midday heat. They emerged to find their world transformed. The sky dark, the air thick with ash, the temperature dropping rapidly from the previous inferno. They are cold now, confused, hungry. The vegetation they depend on is gone, burned to ash or buried under debris. But they are alive. They have survived the worst that the universe can throw at them, or so they believe. Then they hear it, a sound unlike anything in their experience. It is not the roar of a predator or the crack of thunder. It is a continuous, building rumble that seems to come from the earth itself, from the sky, from everywhere at once. The sound grows louder, impossibly louder, until it exceeds the threshold of pain, until it becomes not a sound, but a physical force. The Rabdodon flee from their cave in panic, but there is nowhere to run. The shock wave hits them with the force of a solid wall traveling at the speed of sound. One instant they are running, the next instant they are airborne, tumbling through space like leaves in a storm. They hit the ground dozens of meters away with bone-shattering force. Those that survive the initial impact stagger to their feet, disoriented, bleeding from their ears and noses. The shock wave has ruptured their inner ears, damaged their lungs, caused internal hemorrhaging. But they do not have time to process their injuries. Behind the initial pressure wave comes the wind. This is not wind as we understand it. This is air being physically displaced by the passage of the shock wave, moving at hundreds of kilometers per hour. It picks up everything not anchored to bedrock: trees, boulders, bodies, debris. The landscape becomes a horizontal tornado, a river of solid matter flowing at impossible speeds. The Rabdodon are caught in this maelstrom and simply disintegrate. Their bodies are dashed against rocks, torn apart by the violence of the wind, scattered across kilometers. Within seconds, there is nothing left of them but fragments. This scene is repeating across entire continents. Every creature that survived the thermal pulse now faces the shock wave. Some are killed instantly by the pressure itself. Others die in the winds that follow. A few, those deep underground or those protected by geography, survive. But they are the minority. The vast, overwhelming majority die. In South America, herds of Tyrannosaurs, the largest land animals ever to exist, are toppled like dominoes. These creatures weigh 50 tons or more, their legs like pillars, their necks extending 20 meters into the air. They have no natural predators. Nothing in their world can threaten them. But the shock wave does not care about size or strength. It hits them with force measured in atmospheres of pressure, and they fall. Their immense bodies crash to the ground, crushing smaller animals beneath them, and they cannot rise. Many break their legs in the fall. Others rupture internal organs. They lie on their sides, breathing laboriously, waiting for death. The shock wave propagates through the ocean as well, creating underwater pressure waves that kill with equal efficiency. Deep-sea creatures, adapted to high-pressure environments, find themselves subjected to rapidly fluctuating pressures that exceed even their tolerance. Their swim bladders rupture. Their internal organs collapse. Fish that have evolved over millions of years to survive in the deep ocean die by the millions, their bodies sinking into trenches where they will eventually fossilize, becoming evidence for future scientists trying to understand this day. Closer to the surface, the underwater pressure wave creates a different kind of havoc. It races through the water at over 1,500 meters per second, faster than sound travels through air. Marine reptiles, already stressed by the temperature changes and the choking ash falling from the sky, are hit by a wall of pressure that stuns them, damages their organs, leaves them floating helplessly at the surface. Sharks, ancient and resilient, fare better than most. Their cartilaginous skeletons flex with the pressure changes rather than shattering like bone. Their simple, efficient body plans prove more survivable than the complex, specialized forms of marine reptiles. This is a pattern that will repeat itself throughout the extinction. The specialists die, the generalists survive. Complexity becomes a liability. Simplicity becomes an advantage. But even sharks are dying in vast numbers. The ocean is being thoroughly mixed by the passage of the shockwave, by the tsunamis that continue to circle the globe, by the sudden temperature changes. Deep, cold water is being brought to the surface. Surface warm water is being pushed down. Currents that have flowed in the same patterns for millions of years are disrupted, reversed, or stopped entirely. The entire oceanic circulation system is being scrambled. 60 minutes after impact, the shock wave has circled half the globe. It has crossed the Atlantic Ocean, attenuated somewhat by the lack of solid ground, but still carrying tremendous energy. It makes landfall in Africa, with winds exceeding 500 kilometers per hour. Ancient forests, rainforests that have stood since before the dinosaurs, are flattened in seconds. Not damaged, not knocked down, but completely erased, reduced to splinters. A pack of abelisaurids, medium-sized predatory dinosaurs, is hunting when the shock wave arrives. They are downwind of a herd of sauropods, creeping forward through the undergrowth, preparing to single out a young or weak individual. They are focused, intent, every sense attuned to their prey. They do not notice the wall of destruction approaching from behind until it is too late. The shock wave catches them in the open. The lead abelisaurid is lifted bodily into the air and slammed against a rock face with enough force to shatter every bone in its body. The others try to brace themselves, but it is futile. The wind picks them up and throws them like toys. They tumble through the air, crash into trees, into each other, into the ground. None of them survive. The sauropods they were hunting die too, but more slowly. The shock wave knocks them down, and they fall in a tangle of necks and tails and massive bodies. Some are crushed by their own weight. Others lie helpless, unable to rise, as the secondary effects of the impact begin to manifest. Because the shock wave is not the only killer at work. As it passes, it creates a partial vacuum in its wake, a low-pressure zone that pulls air rushing back toward ground zero. This creates cyclonic winds, vortices kilometers across that spin up spontaneously and then dissipate just as quickly. These wind systems pick up the ash and debris that cover the ground and lift it high into the atmosphere, creating dust storms that would make Mars look clear by comparison. The air becomes unbreathable. It is a thick soup of ash particles, each one a microscopic piece of glass or rock, each one sharp enough to shred lung tissue. Animals that survived the shockwave itself now suffocate, choking on air that has become a solid. They cough, trying to clear their airways, but there is no clear air to breathe. Their lungs fill with fluid. Their breathing becomes labored, then stops. They die with their mouths open, gasping for oxygen that will not come. In Antarctica, which at this time is not a frozen wasteland but a temperate forest, the shock wave arrives after crossing the entire Pacific Ocean. It is weaker here, having traveled the maximum distance from impact, but it is still powerful enough to level forests and kill anything above ground. Polar dinosaurs, species adapted to the long, dark winters of high latitudes, die alongside their tropical cousins. The impact does not discriminate by latitude or climate. It is global, total, absolute. 90 minutes after impact, the shock wave has circled the entire planet. It arrives back at ground zero from the opposite direction, having traveled 40,000 kilometers in 90 minutes. It meets itself, collides with the continuing pressure waves still emanating from the crater and creates a zone of chaotic turbulence where winds blow in every direction at once. But Ground Zero is already dead. Everything within 3,000 kilometers has been sterilized. The rock itself is still glowing hot, radiating heat into the darkness. The crater, 35 kilometers across and 20 kilometers deep, is a bowl of molten stone, a wound in the planet that will take millions of years to heal. The shock wave begins its second trip around the world, but it is weaker now, much of its energy dissipated by friction with the atmosphere, by the work of destruction it has already accomplished. This second passage will kill, but not as efficiently as the first. The third passage will be weaker still. Eventually, after circling the globe perhaps 5 or 6 times, the shock wave will dissipate entirely, its energy spread too thin to cause further damage. But the damage is already done. 90 minutes after impact, perhaps 30% of all species on Earth are extinct. Entire ecosystems have been erased. Food chains have collapsed. The survivors find themselves in a world utterly unlike the one they knew 90 minutes ago. The sky is dark, choked with debris that will block the sun for months. The temperature, which spiked to lethal levels during the thermal pulse, is now dropping rapidly. Without sunlight to warm the surface, the planet is beginning to cool. The fires still burn, millions of them scattered across every continent, but their heat is local, not global. Away from the fires, the temperature is falling, and it will keep falling, because the impact has initiated climate change on a scale that makes human-caused global warming look trivial. The asteroid struck rock rich in sulfur, and the impact vaporized millions of tons of it. That sulfur is now in the atmosphere, combining with water vapor to create sulfuric acid. This acid will fall as rain, poisoning the soil, acidifying the oceans, killing plants that somehow survived everything else. The carbon dioxide from the burning forests is building up in the atmosphere, but its warming effects will be delayed, overwhelmed in the short term by the cooling effects of the dust and sulfur. Earth is heading into an impact winter that will last for months, possibly years. Temperatures will drop below freezing across most of the planet. Any plant that survives the fires and the acid rain will freeze. The dinosaurs, magnificent and diverse, rulers of Earth for 165 million years, are facing extinction. Not all of them will die immediately. Some will survive for days, even weeks. But their world is gone. The food chains they depend on are broken. The climates they are adapted to no longer exist. They are evolutionary dead ends, living fossils in a world that has moved on without them. 90 minutes have passed since the asteroid struck. The age of dinosaurs is over. The age of survival has begun. And in the darkness, in the chaos, in the ruins of a world, the creatures that will inherit the earth are beginning to emerge from their burrows. The acid rain begins. Hours 1.5 to 3. The atmosphere of Earth has become a chemical weapon factory. High above the burning continents, in the stratosphere where passenger jets will one day cruise, a deadly transformation is underway. The impact vaporized not just the asteroid and the bedrock it struck, but also the specific type of bedrock that will make this extinction uniquely catastrophic. The Yucatan Peninsula sits atop massive deposits of anhydrite, a mineral composed of calcium sulfate. Under normal circumstances, This rock is chemically inert, harmless. But normal circumstances ended 90 minutes ago. The impact vaporized an estimated 300 billion tons of anhydrite, releasing 100 billion tons of sulfur into the atmosphere in a matter of seconds. That sulfur is now combining with water vapor to create sulfuric acid, the same acid found in car batteries, the same acid that can dissolve metal and burn through flesh. It is forming in clouds that span continents, in concentrations that would make industrial pollution look benign by comparison. 2 hours after impact, the first drops begin to fall. In what will one day be the American Midwest, a group of ankylosaurs huddles beneath an overhang of rock. These are armored dinosaurs, living tanks covered in bony plates and wielding massive tail clubs that can shatter bone. They have survived the thermal pulse by being in a ravine when it struck, protected by the walls of stone around them. They survived the shock wave by their sheer mass and low center of gravity. They are tough, resilient, built to endure. But they are not built to endure what is about to happen. The rain begins as a light drizzle, almost refreshing after the heat and chaos of the previous hours. The ankylosaurs tilt their heads upward, mouths open, drinking. Water is water, and they are desperately thirsty. The fires have consumed all standing water within kilometers. This rain is the first moisture they have encountered since the world ended. Then the burning starts. The raindrops are not pure water. They are a solution of sulfuric acid with a pH of 2 or lower, acidic enough to etch glass, to dissolve limestone, to burn living tissue on contact. Where the drops hit the ankylosaurus, their armored skin begins to blister. The bony plates that protected them from predators offer no protection against chemistry. The acid seeps into cracks, finds soft tissue, and begins to burn. The ankylosaurs bellow in pain and confusion. They shake their heads, trying to dislodge the water from their mouths, but they have already swallowed. The acid burns their throats, their esophagus, their stomach lining. They vomit, but this only brings the acid back up, burning them twice. Their eyes, vulnerable and exposed, are damaged by the rain. Within minutes, several of them are blind, stumbling in circles, crashing into each other. They try to find shelter, but the rain is everywhere. It falls from a sky choked with sulfur-laden clouds that stretch from horizon to horizon. There is no escape. The acid rain will continue for hours, for days, replenished constantly by the sulfur in the atmosphere mixing with water vapor. The ankylosaurus die slowly, over the course of several hours, from a combination of acid burns, internal hemorrhaging, and shock. Their armor, which made them nearly invincible in the world before, becomes a trap. The acid pools in the crevices between plates, concentrating, burning deeper. They cannot shed their armor. They cannot escape their own bodies. This scene is repeating across the planet. Every animal that survived the initial impact, the thermal pulse, the shock wave, now faces this new threat. The rain is indiscriminate, falling on predator and prey alike, on land and sea, on the dying and those desperately trying to survive. In the oceans, the acid rain has an even more devastating effect. Seawater normally has a pH of around 8, slightly alkaline. This alkalinity is crucial for organisms that build shells or skeletons from calcium carbonate. Ammonites, shellfish, corals, Plankton, pteropods. Their bodies are essentially made of chalk, and chalk dissolves in acid. The rain hitting the ocean surface begins to acidify the water. At first, the effect is localized, confined to the top few meters. But the ocean is being mixed violently by continuing tsunamis, by temperature-driven currents, by the chaos initiated by the impact. The acidic surface water is being pulled down into the depths. The pH begins to drop throughout the water column. An ammonite, one of billions still alive 2 hours after impact, finds that its shell is becoming soft. The beautiful spiral structure that protected it, that gave it buoyancy, that defined its entire existence, is dissolving. The calcium carbonate is reacting with the acid, creating calcium sulfate and carbon dioxide. Bubbles form on the surface of the shell. The structure weakens. The ammonite tries to dive deeper, seeking safety in the depths, but the pressure at depth requires a strong shell. Its weakened shell cannot withstand the pressure. It implodes, and the ammonite dies. This is happening to ammonites everywhere. All of them. Every species, every population, every individual. The ammonites, which have existed for 350 million years, which survived every extinction event since the Devonian period, which diversified into thousands of species and filled every oceanic niche, are being wiped out completely. Within a week, they will be extinct. Not endangered, not rare, extinct, gone forever. The same fate awaits other shell-building organisms. The ocean is experiencing a mass die-off of unprecedented scale. The planktonic organisms that form the base of the marine food chain, the microscopic creatures that create oxygen through photosynthesis, that feed everything from tiny fish to massive whales, are dissolving. Their calcium carbonate shells are falling apart. Without shells, they cannot survive. They die, in their trillions upon trillions, their bodies raining down through the water column in a phenomenon scientists will later call marine snow. But this is not gentle snow. This is the collapse of oceanic ecosystems. The fish that feed on plankton find nothing to eat. They starve. The larger fish that feed on smaller fish find their prey disappearing. They starve. The marine reptiles that feed on fish find the oceans empty. They starve. The entire marine food web is collapsing from the bottom up. On land, the acid rain is destroying what little vegetation survived the fires. Plants that were burned but not killed, that retained living roots and might have regrown, are being poisoned. The acid soaks into the soil, lowering its pH, killing the bacteria and fungi that plants depend on for nutrient uptake. Seeds that might have sprouted and repopulated the scorched earth are being destroyed in the ground. A small grove of ferns in a sheltered valley, somehow untouched by fire, is being dissolved by the rain. The fronds turn yellow, then brown, then black. They curl up and fall from their stems. The stems themselves begin to weaken as the acid breaks down their cell walls. Within hours, the grove is reduced to a mass of rotting vegetation. The smell of decay is overwhelming, mixing with the smell of burning from the distant fires and the acrid smell of sulfur from the rain itself. 3 hours after impact, the rain is falling across 60% of Earth's surface. The remaining 40% will experience it within the next few hours, as the sulfur clouds spread globally on the winds. There is nowhere that will escape. The impact was in the Western Hemisphere, but the devastation is planetary. In shallow lakes and ponds, the acid rain is creating a different kind of horror. These bodies of water have no connection to the ocean, no buffering capacity, no way to dilute the incoming acid. The pH drops rapidly from 7 or 8 down to 4, then 3. This is equivalent to vinegar. Nothing can survive in these conditions. Amphibians, salamanders, and early frogs die in their thousands. Their permeable skin, which allows them to absorb oxygen directly from water, now allows acid to enter their bodies. They cannot escape to land because the land is equally poisoned. They cannot go deeper because shallow ponds have no deeper. They float to the surface, dead or dying, their skin sloughing off, their bodies beginning to decompose even before death is complete. Freshwater fish experience the same fate. The acid damages their gills, preventing oxygen uptake. They suffocate in water, a slow and agonizing death. The smaller fish die first, their higher surface area to volume ratio making them more vulnerable. The larger fish survive longer, but survival is measured in hours, not days. But there are survivors. Deep underground, in caves and burrows and cracks in the bedrock, creatures are sheltering from the rain. Small mammals, no larger than rats, have instinctively gone to ground. They can hear the rain falling outside their burrows. They can smell the acrid fumes, but they do not emerge. Some instinct, some survival mechanism honed over millions of years tells them to stay hidden. These mammals have certain advantages that dinosaurs lack. They are small, requiring less food and water. They are warm-blooded, able to maintain body temperature in changing conditions. They are generalists, able to eat almost anything: plants, insects, carrion, seeds. They are nocturnal, adapted to darkness and cold. And crucially, they can shelter underground, can fit into spaces too small for dinosaurs, can wait out the worst of the catastrophe. They are frightened, hungry, confused, but they are alive. And in the ruins of the Cretaceous world, being alive is enough. Some dinosaurs are also surviving, at least for now. Small theropods, the bird-like dinosaurs that will eventually give rise to true birds, are sheltering in tree hollows and rock crevices. They are small enough to fit into protected spaces, fast enough to have fled from the initial devastation, adaptable enough to survive on insects and carrion when their normal prey is unavailable. A small troodon, a human-sized predator with large eyes and a relatively large brain, sits in a cave watching the rain fall outside. It is injured, one leg broken in the chaos of the shockwave, but it is conscious and aware. It does not understand what has happened. Its brain, sophisticated by dinosaur standards, is still not capable of comprehending planetary catastrophe. But it knows the world has changed. It knows that everything is wrong. The troodon is hungry. It has not eaten in hours. Its metabolism, higher than that of larger dinosaurs but still reptilian, demands food. Outside the cave, it can smell death. Thousands of bodies, animals that died from the shock wave or the thermal pulse or the acid rain, are decomposing in the darkness. The smell should trigger its hunting instinct, should drive it to feed. But the troodon does not leave the cave. Some deeper instinct is warning it that the outside is dangerous, that the rain is death, that shelter is survival. It stays in the cave, hungry and hurting, but alive. 3 hours after impact, The full scope of the catastrophe is becoming clear. This is not a regional disaster. This is not even a continental disaster. This is a global mass extinction in progress. The mechanisms of death are multiple and overlapping. Thermal radiation, pressure waves, acid rain, fire, temperature shock, ecosystem collapse. Each one alone would be devastating. Together, they are unstoppable. The strong are dying alongside the weak. The adapted are dying alongside the generalized. Size offers no protection. Armor offers no protection. Speed offers no protection. The only things that matter are location and luck. Being in the right place when the impact occurred. Being underground during the thermal pulse. Being small enough to shelter, generalized enough to survive on whatever scraps remain. The age of giants is over. The age of specialists is over. The age of apex predators who ruled entire continents is over. The future belongs to the small, the hidden, the flexible, the desperate survivors huddling in the darkness, waiting for a dawn that may never come. Because the worst is still ahead. The acid rain will continue for days. The fires will burn for weeks. The darkness will last for months. And when the darkness finally lifts, the survivors will emerge into a world that bears no resemblance to the one that existed 3 hours ago. 3 hours have passed since the asteroid struck. Half of all species on Earth are gone. And the dying has only just begun. Darkness at noon, hours 3 to 6. The sun should be high in the sky now, but no one on Earth can see it. The debris cloud from the impact has spread across the entire planet, a shroud of pulverized rock and ash that blocks virtually all sunlight from reaching the surface. At ground level, the darkness is nearly absolute. This is not the darkness of night, where eyes can adjust and stars provide faint illumination. This is the darkness of deep caves, of ocean trenches, of burial. The temperature is dropping rapidly. Without sunlight to warm the surface, Earth is radiating heat into space with nothing to replace it. In the first 3 hours after impact, the global average temperature has already fallen by 15 degrees Celsius. In regions far from the equator, far from the still burning fires, the temperature is approaching freezing, and it will continue to fall for weeks. 4 hours after impact, in what will one day be Western North America, a herd of Pachycephalosaurus struggles through the darkness. These are dome-headed dinosaurs, their skulls thickened into battering rams used for combat and display. Before the impact, they were thriving, feeding on the low vegetation of open woodlands, competing for mates in ritualized headbutting contests. Now they are simply trying to stay alive. The herd has been moving constantly since the shock wave passed, driven by instinct to flee from danger that is everywhere and nowhere. They cannot see where they are going. The darkness is so complete that they navigate by sound and smell alone, following each other's calls, trying desperately to stay together. To be separated from the herd in this darkness means death. One of them stumbles into a gully and breaks its leg. The sound of the bones snapping is audible even over the constant background noise of distant fires and falling debris. The injured animal tries to stand, fails, tries again. Its packmates hear its distress calls and pause, uncertain. In the world before, they might have stayed with the injured member, might have defended it from predators, might have given it time to heal. But there is no time now. The herd is already stressed beyond endurance. They are cold, hungry, terrified. The injured Pachycephalosaurus calls out again, a desperate plea for help that will not come. The herd moves on, leaving it behind. The injured animal's calls continue for several hours, growing weaker before finally stopping. It dies alone in the darkness from exposure and shock, and the simple fact that its body can no longer cope with the cascade of failures overwhelming it. This abandonment is happening everywhere. Social bonds, family groups, the complex behaviors that evolved over millions of years, all of it is breaking down under the pressure of survival. Herding animals scatter. Parents abandon young. Predators ignore prey they can smell but not see, too exhausted or injured to hunt. The darkness is doing something even more insidious than simply hiding threats and obstacles. It is shutting down photosynthesis. Every plant on Earth, from the tallest tree to the smallest algae, depends on sunlight to produce energy. Without light, they cannot photosynthesize. Without photosynthesis, they begin to die. At first, this is not obvious. Plants have energy reserves. They can survive without sunlight for hours, even days. Large trees can survive for weeks on stored sugars, but the clock is ticking. Every minute without sunlight depletes those reserves a little more. And with the acid rain still falling, with the soil poisoned, with their roots damaged by the temperature extremes, the plants are under assault from multiple directions simultaneously. 5 hours after impact, the first plants begin to die in significant numbers. These are the small, fast-growing species with minimal energy reserves. Grasses, flowers, small ferns. They turn brown, wilt, collapse. In the darkness, no one can see this happening, but the smell is there. The acrid smell of rotting vegetation mixing with all the other smells of catastrophe. The death of plants has immediate consequences for herbivores. A triceratops, wandering blind through the darkness, finds a stand of cycads and begins to feed. But the cycads are already dying, their leaves toxic with accumulated stress compounds, their tissue breaking down. The triceratops eats anyway, driven by hunger that has become all-consuming. It does not know that the food is poisoned, that the dying plant tissue contains compounds that will make it sick. An hour later, the triceratops is lying on its side, gut-bloated, in extreme distress. The food it ate is fermenting in its massive digestive system, producing gas that cannot escape, causing pain that it has no framework to understand. It tries to vomit, but cannot. Its digestive system, designed for processing huge quantities of tough plant matter, is now working against it. The triceratops dies from a combination of poisoning and bloat. An ignominious end for an animal that survived 66 million years of evolution. In the oceans, the darkness is creating a different kind of crisis. The phytoplankton, microscopic plant-like organisms that form the base of the marine food chain, need sunlight just as much as land plants do. Without it, they begin to die within hours. These organisms are responsible for producing more than half of Earth's oxygen. Their death will have consequences far beyond the immediate extinction event. As the phytoplankton die, they sink. Their bodies drift down through the water column, joining the bodies of ammonites and fish and marine reptiles in a constant rain of organic matter. This debris settles on the ocean floor, where bacteria begin to decompose it. But decomposition consumes oxygen, and with no photosynthesis occurring at the surface, that oxygen is not being replaced. The ocean is beginning to suffocate. In the deep waters, in the mid-depths, oxygen levels are dropping rapidly. Fish and other marine organisms that survived the initial impact, the pressure waves, the acid rain, now face anoxia, oxygen starvation. They swim toward the surface, seeking the oxygen-rich surface waters, but the surface is also depleted. There is nowhere to go. A mosasaur, one of the last of its kind, surfaces to breathe and finds itself in a dying ocean. The water around it is thick with floating debris, dead fish, dying plankton, ash and pumice from the impact. The air above the water is barely better, thick with sulfurous fumes and ash particles. The mosasaur breathes anyway, because the alternative is drowning. But each breath damages its lungs a little more. This mosasaur is 12 meters long, an apex predator that has known no fear in its adult life. It has hunted in these waters for 20 years, feeding on fish and smaller marine reptiles, dominating its territory. Now it is starving. The fish are gone. The other marine reptiles are dead or dying. The ocean is empty. The mosasaur dives, searching for prey in the depths. Its eyes, adapted for the dim light of deep water, can see almost nothing in the darkness. It navigates by sensing vibrations in the water, by smell, by instinct. It detects something, follows it, finds a dead plesiosaur sinking slowly toward the bottom. The mosasaur begins to feed, tearing chunks from the corpse, swallowing them whole. But the meat is already rotten, already toxic with decomposition. The mosasaur does not care. It is too hungry to care. It feeds until it can eat no more, then surfaces again, bloated and sick. It will die within hours, poisoned by its own desperation. 6 hours after impact, the global ecosystem is in complete collapse. The food chains that took millions of years to evolve are breaking down in hours. Herbivores cannot find plants to eat. Carnivores cannot find herbivores to hunt. Scavengers find plenty of corpses, but many are too toxic to consume. Starvation is becoming the dominant cause of death, replacing the more immediate killers of the first few hours. But some creatures are adapting, finding ways to survive in this new nightmare world. The small mammals in their burrows are venturing out briefly to feed. They cannot see in the darkness, but they do not need to. They navigate by smell and touch and hearing, senses that work just as well in darkness as in light. They find dead insects, seeds, bits of charred vegetation. They eat quickly and return to their burrows. They are surviving. Some small dinosaurs are doing the same. A pair of Bambiraptor, tiny predatory dinosaurs no larger than chickens, emerge from a crack in the rocks where they have been sheltering. They are starving, their high metabolism demanding constant food. They move through the darkness with surprising confidence, their large eyes useless, but their other senses sharp. They find the body of a larger dinosaur and begin to feed, tearing at the softest tissue with their small teeth. The meat is days old, already decomposing, but the Bambiraptor do not care. They have eaten carrion before. Their digestive systems can handle it. They feed for several minutes, eating as much as they can hold, then retreat back to their shelter. They will survive this night and perhaps many more. They are small, adaptable, opportunistic. These are the traits that matter now. In the sky, or what used to be the sky, flying creatures are facing their own apocalypse. Pterosaurs, which have dominated the aerial realm for over 150 million years, are dying en masse. They cannot fly in the darkness. They cannot navigate without seeing. They cannot hunt. Many have already crashed into the ground or into obstacles, dying from impact trauma. Others have landed and are unable to take off again, stranded in a world they are not equipped to navigate on foot. A Quetzalcoatlus, one of the largest flying animals ever to exist, stands alone in the darkness. Its wingspan of 12 meters is useless without light to see by, without updrafts to soar on. It is a creature designed for flight, not for walking on the ground. Its legs are weak, its body ungainly without the air to support it. It takes a few awkward steps and stops, disoriented and exhausted. The Quetzalcoatlus is hungry and cold. Its thin wing membranes, stretched between elongated finger bones, are losing heat rapidly. It tries to fold its wings close to its body for warmth, but cannot maintain its temperature without food. It stands motionless in the darkness, conserving what little energy it has left, hoping for a dawn that will not come. By 6 hours after impact, the temperature has dropped below freezing across much of the planet. The fires still burn in many areas, creating pockets of heat. But away from the flames, the cold is deadly. Water is freezing in ponds and streams. Dew freezes on rocks and dead vegetation. The air itself feels solid, thick with ash and moisture that is condensing into an acidic sleet. Animals adapted to tropical and subtropical climates are dying from hypothermia. Their bodies, designed to shed heat in warm environments, cannot conserve it in freezing conditions. They grow sluggish, confused, their movements slow, their hearts slow. They lie down, intending to rest for a moment, and never get up again. A Parasaurolophus, a large duck-billed dinosaur with an elaborate crest on its head, is dying from cold. 6 hours ago, it was part of a herd of 50 individuals. Now it is alone, separated from the others in the darkness and chaos. It has burns on its back from the thermal pulse. It has acid burns on its skin from the rain. It has internal injuries from the shock wave. And now it is freezing to death. The Parasaurolophus lies on its side, breathing shallowly. Its breath forms clouds of vapor in the freezing air, visible even in the darkness as faint glows from distant fires reflect off the moisture. Its body temperature is dropping below the threshold needed for brain function. It is slipping into unconsciousness, into hypothermic shock, into death. In its final moments, the Parasaurolophus makes one last sound, a low, mournful call from the resonating chamber in its crest. The sound carries across the darkened landscape, a farewell to a world that no longer exists. No other Parasaurolophus answers. Perhaps there are none left alive to answer. The sound fades into the darkness, and the animal dies. 6 hours have passed since the asteroid struck. The Earth is unrecognizable. The blue-green planet that existed this morning is now shrouded in darkness, its surface scarred by fire, its oceans acidified and dying, its temperature plummeting. An estimated 60 to 70% of all species are now extinct. The rest are dying. But in the darkness, in the ruins, the future is taking shape. The survivors are not the strongest, or the largest, or the most specialized. They are the small, the hidden, the adaptable. They are the creatures that can eat anything, live anywhere, survive on scraps and darkness and cold. They are inheriting a dead world, but it is a world that will, eventually, live again. The survivors emerge, hours 6 to 9. The darkness is not uniform across the planet. Near the equator, where fires still rage across entire continents, the sky glows with an eerie orange light that filters through the ash and debris. The heat from these fires creates updrafts that punch through the debris cloud, creating brief columns of slightly clearer air. The temperature here remains above freezing, even hot in some areas. But this is not mercy. This is a different kind of hell. 7 hours after impact, in what will one day be South America, the fires have merged into a single continental conflagration. The flames stretch from horizon to horizon, consuming everything combustible. The heat is so intense that rock itself is cracking, exploding from thermal stress. The sound is a constant roar, like standing next to a waterfall, but instead of water, it is burning air. Superheated gases rushing upward at hundreds of kilometers per hour. Nothing lives here anymore. This is a zone of total sterilization. Even bacteria are dying, cooked by temperatures that exceed 200 degrees Celsius in some areas. The ground is covered in a layer of white ash several meters deep. Beneath the ash, the soil has been baked into a ceramic-like substance, all organic matter consumed, all nutrients destroyed. When the fires finally burn out, weeks from now, nothing will grow here for years. But at the edges of the fire zone, in the transitional areas where the flames have not yet reached or have already passed, creatures are making desperate decisions. A family group of small mammals, shrew-like insectivores, faces an impossible choice. Behind them, the fire is advancing. The heat is already unbearable. Ahead of them lies darkness and cold and uncertainty. They hesitate, their simple brains struggling with a decision their ancestors never faced. The fire makes the decision for them. A wall of flame surges forward, driven by sudden winds, and the mammals run. They flee into the darkness, away from the heat and light, into territory they do not know. They run blindly, squeaking to maintain contact with each other, their tiny hearts hammering with terror and exertion. Behind them, the fire consumes the burrow where they raised their young, the territory they defended, every familiar landmark of their lives. They run for an hour, perhaps more, until exhaustion forces them to stop. They huddle together in a shallow depression, sharing body heat, panting. They are cold now, far from the fire's warmth. They are hungry. They are lost. But they are alive. And in this new world, that is the only victory that matters. 8 hours after impact, patterns are beginning to emerge in the chaos. The survivors are not random. They share certain characteristics, certain adaptations that make the difference between extinction and survival. Size is one factor. Small animals, those weighing less than 25 kilograms, are surviving at much higher rates than large animals. They need less food, can shelter in smaller spaces, can survive on resources that larger animals would ignore. A small crocodilian, no more than 2 meters long, has survived by retreating to a river and submerging itself in the mud at the bottom. Crocodilians have a trick that most reptiles lack. They can slow their metabolism to almost nothing, can survive without breathing for hours by switching to anaerobic respiration. This crocodilian has been underwater since the thermal pulse, insulated by mud and water from the worst of the heat. Now, 8 hours later, it surfaces cautiously. The river is very different from what it remembers. The water is warm, almost hot, heated by the thermal pulse and by burning vegetation that fell into it. The surface is covered with ash and dead fish. The banks are charred, but the river still flows. Water still exists, and where there is water, there is hope. The crocodilian hauls itself onto the bank and lies still, conserving energy, waiting. Its kind have survived extinction events before. They survived the Permian extinction, the worst mass dying in Earth's history. They survived the Triassic extinction that killed most of their competitors. They will survive this too. They are generalists, able to eat anything from fish to carrion to vegetation if necessary. They are cold-blooded, requiring a fraction of the food that warm-blooded animals need. They are patient, able to wait weeks between meals. These traits, unremarkable in the world before, are priceless now. In the oceans, a different kind of survivor is emerging. Sharks, those ancient predators that predate the dinosaurs by hundreds of millions of years, are proving remarkably resilient. Their cartilaginous skeletons flexed with the pressure waves instead of shattering. Their simple body plans required less food than the more specialized marine reptiles. Their ability to detect dying prey from kilometers away through electrical and chemical signals is giving them access to food sources other predators cannot find. A tiger shark, 5 meters long, cruises through water clouded with debris and decomposition. It is hungry, having not eaten in 2 days, but it is not desperate. Not yet. Its senses detect the faint electrical signals of a dying plesiosaur 50 meters away. The shark turns toward the signal and accelerates. The plesiosaur is floating at the surface, too weak to dive, dying from a combination of starvation and acid burns. It sees the shark coming, but cannot flee. It does not even try. The shark attacks, biting into the plesiosaur's soft underside, tearing away chunks of flesh. The plesiosaur dies quickly, a mercy in this merciless time. The shark feeds until it is full, then descends into deeper water to digest. It will survive this extinction event. Its descendants will swim in Earth's oceans for millions of years to come, barely changed, a living link to the world that died today. 9 hours after impact, the first survivors are beginning to emerge from their shelters in significant numbers. The immediate threats have passed. The thermal pulse is over. The shock wave has dissipated. The acid rain has stopped in many areas, the sulfur clouds having dumped most of their payload. What remains is a transformed world, but one that can be cautiously explored. A small feathered dinosaur, a member of the group that will eventually give rise to modern birds, crawls out of a rock crevice where it has been hiding. This animal is the size of a crow, covered in primitive feathers that provide insulation against the cold. It has a beak instead of teeth, an adaptation that will prove crucial to its survival. Beaked animals can eat a wider variety of foods: seeds, insects, carrion, even small amounts of vegetation. They are not locked into a single dietary strategy like specialized predators or herbivores. The dinosaur hops cautiously across the ash-covered ground, its head swiveling constantly, alert for danger. But there are no predators here. The predators are dead. A Tyrannosaurus that once ruled this territory lies 100 meters away, a charred corpse already being consumed by insects and bacteria. The small dinosaur approaches the corpse fearlessly and begins to feed, pecking at the soft tissue around the eyes and mouth. This is a profound role reversal. In the world before, this small creature would have fled at the mere scent of a tyrannosaur. Now it feeds on one with impunity. The mighty have fallen. The meek are inheriting the earth. But the meek are still struggling. 9 hours after impact, the survivors are facing a critical shortage of food and water. The fires have consumed or contaminated most food sources. The acid rain has poisoned much of the remaining water. Animals that survived the initial catastrophe are now dying more slowly from starvation and dehydration. A herd of Edmontosaurus, perhaps 20 individuals, has gathered around a small spring that still produces clean water. They are the remnants of a herd that once numbered 300. They are burned, injured, starving, but they are alive and desperate to stay that way. They drink deeply, instinctively knowing that water is life, that without it, they have no chance. But the spring is failing. The aquifer that feeds it has been disrupted by the shockwave. The flow is decreasing by the hour. By tomorrow, it will be dry. The Edmontosaurus do not know this. They cannot plan for it. They can only drink while water remains and hope. Near the spring, conflicts are beginning to emerge. A small mammal approaches to drink and is chased away by an Edmontosaurus. The hadrosaur, normally a peaceful herbivore, has become aggressive in its desperation. It will not share this precious resource with potential competitors, no matter how small. The mammal retreats, but does not give up. It waits in the darkness, patient, until the hadrosaurs move away from the spring to rest. Then it darts in, drinks quickly, and vanishes back into the shadows. This is the new dynamic of survival. Patience, stealth, opportunism. The bold and the aggressive are dying. The cautious and flexible are surviving. Underground, in a network of tunnels and chambers, a colony of small burrowing mammals has survived almost intact. These are not sophisticated creatures. They are roughly equivalent to modern shrews, with simple social structures and basic behaviors. But they have advantages that more advanced animals lack. They live underground, protected from temperature extremes and radiation. They are omnivorous, able to eat roots, insects, fungi, whatever they can find. They are social, able to share body heat and information about food sources. The colony emerges from its burrows as a group, perhaps 50 individuals moving together through the darkness. They spread out, searching for food, calling to each other with high-pitched squeaks. They find a cache of seeds that were buried by a small dinosaur months ago, before the world ended. The dinosaur that buried them is dead, but its foresight is now feeding the mammals. They dig up the seeds and carry them back to their burrows, storing them against the lean times ahead. This is one of the keys to survival: the ability to store resources, to plan, however primitively, for the future. The mammals are doing this instinctively, driven by behaviors evolved over millions of years. But those behaviors are saving them now. In the canopy of a forest that somehow survived the fires, a small, primate-like creature clings to a tree branch. This is one of the earliest primates, a tiny insectivore with grasping hands and forward-facing eyes. It is cold, hungry, frightened. The tree it lives in is dying, its leaves gone, its bark cracked and weeping sap. But the tree is still standing, and that makes it safer than the ground. The primate notices movement in the darkness below and freezes, instinctively hiding from potential predators. But the movement is not a predator. It is a small theropod dinosaur, injured and dying, stumbling through the darkness. The primate watches as the dinosaur falls, tries to rise, falls again, and lies still. After several minutes of motionless observation, the primate descends from its tree. It approaches the dinosaur cautiously, ready to flee at any sign of movement. But the dinosaur is dead. The primate begins to feed, using its hands to tear small pieces of flesh from the corpse. This is not normal behavior for this species. They are insectivores, not scavengers. But normal behavior is a luxury that no longer exists. Adapt or die. The primate is adapting. 9 hours after impact, the scope of the extinction is becoming clear. The largest animals are gone. The specialized predators are gone. The dominant herbivores are gone. What remains is a collection of small, generalized, opportunistic creatures that are rewriting the rules of survival with every hour that passes. But the crisis is far from over. The darkness will continue for weeks. The temperature will keep dropping. The food supply will continue to dwindle. Many of the current survivors will not make it another day, another week, another month. The extinction event is not a single catastrophe. It is a cascade of catastrophes, each one claiming more victims, each one testing the limits of survival. In the ruins of the old world, in the darkness and the cold and the ash, life is clinging on by its fingernails. The dinosaurs are dying. The ammonites are gone. The marine reptiles are extinct. The pterosaurs have vanished from the skies. 75% of all species on Earth are already extinct or doomed. But life itself is not dying. Life is adapting, surviving, waiting. In burrows and caves and cracks in the rocks, in the deep ocean and in the ashes of burned forests, the seeds of the future are germinating. They are small seeds, humble seeds, but they are all that remains, and from them, given millions of years, will grow a new world. The ocean dies. Hours 9 to 12. The ocean, which covers 70% of Earth's surface, has always been a buffer against catastrophe. Its immense volume moderates temperature changes. Its chemistry resists acidification through natural buffering systems. Its depths provide refuge from surface disturbances. For billions of years, when the land became uninhabitable, life retreated to the sea and survived. But not this time. This time, the ocean is dying. 10 hours after impact, the full scope of the marine extinction is becoming apparent. The surface waters, once teeming with life, are now a graveyard. Dead plankton, dead fish, dead ammonites, dead everything floats in a thick soup of organic matter. The smell, if anyone were there to smell it, would be overwhelming. The stench of billions of tons of decomposing flesh, mixed with sulfur from the acid rain and the acrid smell of ash. A sea turtle, one of the few marine reptiles still alive, surfaces in this death zone. Sea turtles have advantages that other marine reptiles lack. They can hold their breath for hours, limiting their exposure to the toxic surface air. They have hard shells that protected them from the pressure waves. They are omnivorous, able to eat jellyfish, seaweed, or carrion as circumstances demand. But even these advantages are not enough. The turtle surfaces and immediately begins to struggle. The water at the surface is thick with ash and debris. It clogs the turtle's nostrils, irritates its eyes, makes breathing difficult. The turtle dives again, seeking cleaner water. But there is no clean water. The debris extends down through the water column for dozens of meters. The turtle swims through clouds of dead plankton, through forests of sinking ammonite shells, through the disintegrating bodies of fish. It needs to breathe. It surfaces again, gasps desperately, and dives once more. Its lungs are damaged now, contaminated with ash and acidic water vapor. Each breath is becoming harder than the last. The turtle swims toward what its instincts tell it should be a coastline, some place where it might crawl onto land and rest. But the coastline has been obliterated by tsunamis. There is no beach, no refuge, only churning water filled with death. The turtle dies slowly over the next several hours, its respiratory system gradually failing, its body weakening until it can no longer dive. It floats at the surface, still alive but unable to submerge, unable to escape the toxic air. Eventually, its lungs give out completely, and it drowns in water it has lived in all its life. This scene is repeating across all of Earth's oceans. The marine reptiles, which have ruled the seas for over 100 million years, are going extinct in a matter of hours. Mosasaurs, plesiosaurs, sea turtles, marine crocodilians, all of them are dying. Some from direct impact effects, some from starvation as their prey disappears, some from the toxic conditions in the water and air, but all of them are dying. 11 hours after impact, the ocean is experiencing a phenomenon that will later be called a dead zone, or anoxic event. The decomposition of billions of tons of dead organisms is consuming all available oxygen in the water. Bacteria are thriving in this feast of death, multiplying exponentially, their populations exploding. But bacterial respiration requires oxygen, and they are using it faster than it can be replenished. Without photosynthesis occurring at the surface, no new oxygen is being produced. The ocean is suffocating from the bottom up and the top down simultaneously. Fish that survived everything else are now dying from anoxia. They swim desperately toward the surface, mouths gaping, gills working frantically, trying to extract oxygen from water that contains almost none. A school of primitive fish, distant ancestors of modern teleosts, breaks the surface in their desperation. They leap from the water like flying fish, trying to breathe air. But their gills are not designed for this. They fall back into the water and try again, driven by suffocation to attempt the impossible. One by one, they weaken and die, their bodies joining the countless others floating in the toxic soup. But some fish are surviving. Those with the ability to breathe air, even partially, have a crucial advantage. Lungfish, which possess both gills and primitive lungs, can surface and gulp air directly. They are suffering from the acid rain and the toxic atmosphere, but they can survive it in ways that purely gill-breathing fish cannot. A lungfish in what will one day be Australia has burrowed into the mud of a drying riverbed. It has entered a state of estivation, a form of suspended animation that allows it to survive drought. Its metabolism has slowed to a fraction of normal. It is breathing air through a small tunnel in the mud, taking one breath every few minutes. The air is toxic, the mud is acidic, but the lungfish endures. It can remain in this state for months if necessary. It will outlast the darkness. In the deep ocean, in the trenches and abyssal plains far from sunlight, creatures are facing their own crisis. These organisms never depended on photosynthesis directly. They survive on the constant rain of organic matter from the surface, the marine snow of dead plankton and feces and molted shells that drifts down from the sunlit zone. This rain has sustained deep-sea ecosystems for hundreds of millions of years. But now, the rain has become a deluge. The sheer volume of dead matter sinking from the surface is overwhelming. It piles up on the seafloor in drifts meters thick. The bacteria decomposing this matter are consuming all available oxygen, creating anoxic zones even in the deep ocean. Creatures that have never encountered low oxygen conditions in their entire evolutionary history are suffocating in the depths. A vampire squid, a deep-sea cephalopod with bioluminescent displays, and a lifestyle adapted to the oxygen minimum zone, finds that its refuge has become a death trap. The oxygen levels in its normal depth range have dropped below even its impressive tolerance. It swims upward, seeking better conditions, but the entire water column is depleted. There is nowhere to go. The squid dies at a depth of 600 meters, its body sinking back to the seafloor it tried to escape. 12 hours after impact, the ocean's thermohaline circulation, the great conveyor belt of currents that moves water around the globe, is beginning to break down. This circulation is driven by differences in temperature and salinity. Cold, salty water in polar regions sinks and flows toward the equator. Warm, fresh water at the equator rises and flows toward the poles. This system regulates global climate, distributes nutrients, and has operated continuously for millions of years. But the impact has disrupted everything. The massive influx of vaporized rock and water has changed salinity patterns. The temperature shock has altered the density of water masses. The tsunamis have mixed surface and deep water in chaotic patterns. The circulation is stuttering, slowing, in some areas stopping entirely. This has immediate consequences. Nutrients that normally well up from the depths supporting surface productivity are no longer rising. Areas that were nutrient-rich and productive yesterday are becoming oceanic deserts. Not that it matters in the short term with the surface already dead, but it will matter in the months and years to come. The ocean's recovery will be delayed by decades because of this circulation failure. On the seafloor, in the shallows and the depths, a different kind of extinction is occurring. The benthic organisms, creatures that live on or in the ocean floor, are being buried alive. The impact kicked up trillions of tons of sediment. The tsunamis scoured coastlines and carried the debris out to sea. All of this material is now settling, creating a blanket of sediment that smothers everything it covers. A coral reef, which has been growing slowly for thousands of years, disappears under meters of sediment in hours. The corals, already stressed by temperature changes and acidification, cannot survive burial. They die, their calcium carbonate skeletons adding to the sediment layer, becoming part of the geological record of this catastrophic day. Sea urchins, starfish, bottom-dwelling fish, all of them are being buried. Some try to dig themselves out, to reach the surface of the sediment, but the sediment keeps falling. Eventually, they run out of energy or oxygen and die in place. Future geologists will find their fossils in a distinct layer of sediment that circles the globe, a permanent marker of the day the world ended. But not everything is dying. In the deepest parts of the ocean, around hydrothermal vents where superheated water rich in minerals spews from cracks in the seafloor, life continues almost unchanged. These ecosystems do not depend on sunlight. They are powered by chemical energy, by bacteria that can metabolize sulfur and other minerals. The creatures here, tube worms and vent crabs and strange fish, are isolated from surface conditions by kilometers of water. The impact has sent shockwaves through the ocean that disturbed even these deep communities, but they are recovering. The vents still flow. The bacteria still metabolize chemicals. Life persists in the darkness, as it always has, independent of the sun. These vent communities are tiny oases in a dying ocean, but they are proof that life can survive anything if it is adaptable enough, isolated enough, lucky enough. 12 hours after impact, 90% of all marine species are extinct or doomed to extinction. The ocean has become a toxic, oxygen-depleted wasteland. The food chains have collapsed. The great marine reptiles are gone. The ammonites, which survived every previous extinction event for 350 million years, are extinct. The reef systems are dead. The productive coastal zones are scoured clean. But in the darkness and the death, survivors persist. Sharks continue to hunt, feeding on the abundance of corpses. Lungfish hide in the mud, waiting. Deep-sea communities around hydrothermal vents continue their alien existence. And countless species of small, hardy, generalized fish are finding ways to survive on the margins, in the pockets of less toxic water, in the rare areas where oxygen still exists. The ocean will take millions of years to recover from this day. The diversity that existed 12 hours ago will never return, not in the same form. New species will evolve to fill the empty niches, but they will be different species, descended from the survivors, adapted to a different ocean. The Mesozoic marine ecosystem, with its giant reptiles and its ammonites and its unique fish, is gone forever. But the ocean itself will survive. Water still covers 70% of the planet. Chemistry still operates by the same laws. Evolution still functions. The ocean is dying, but it is not dead. And from the survivors, from the small and the hardy and the fortunate, new diversity will eventually bloom. 12 hours have passed since the asteroid struck. The ocean is a graveyard, but graveyards can become gardens given enough time. The seeds of that future garden are scattered across the dying ocean, waiting for conditions to improve, waiting for the darkness to lift, waiting for their chance to inherit a new world. The long night falls, hours 12 to 16. 13 hours after impact, the planet has entered what will later be called impact winter. The debris cloud has spread across the entire globe, a shroud of pulverized rock, soot, and sulfur compounds that blocks 99% of all sunlight. The darkness is not temporary. It will last for months, possibly years. And with the darkness comes cold that will transform Earth from a greenhouse world into an icebox. The global average temperature has already dropped by 25 degrees Celsius from pre-impact levels. In regions far from the equator, far from the still burning fires, the temperature is now well below freezing. Ice is forming on lakes and rivers. Snow, mixed with ash and sulfur, is beginning to fall. This is snow that no living creature on Earth has ever experienced, because this world has known no ice caps, no glaciers, no winter as we understand it, for millions of years. A herd of hadrosaurs, perhaps the last of their species, huddles together for warmth in a shallow valley. There are only 12 of them left from a population that once numbered in the thousands. They are pressed against each other, trying to share body heat, but it is not enough. Their bodies, designed for a warm climate, for temperatures of 25 to 30 degrees Celsius, cannot cope with the cold now gripping the land. These are cold-blooded animals, or, at best, with a metabolism somewhere between cold-blooded reptiles and warm-blooded mammals. They cannot generate enough internal heat to maintain their body temperature in freezing conditions. As the temperature drops, their metabolism slows. Their movements become sluggish. Their thoughts, such as they are, become confused and dim. One by one, they begin to die. The youngest dies first, its smaller body losing heat faster than the adults. It simply lies down and does not get up again. Its body temperature drops below the threshold needed for brain function. It slips into unconsciousness and dies within minutes. The other hadrosaurs do not react. They are too cold themselves to notice or care. By 14 hours after impact, all 12 are dead, frozen in place in a huddled group. They will remain there, perfectly preserved by the cold, until the temperature eventually rises and decomposition can begin. Future paleontologists will find them exactly as they died, a snapshot of the final moments of a species that ruled the world for millions of years. This scene is repeating across the planet. Every large dinosaur species that survived the initial impact is now facing the cold, and they are losing. The physics are brutal and unforgiving. Large bodies have less surface area relative to their volume, which normally helps them retain heat. But when the external temperature is far below their viable range, this becomes irrelevant. They cannot generate enough internal heat to compensate for the losses. They freeze. The smaller dinosaurs, those under 20 kilograms, have better chances. Their higher surface area to volume ratio means they lose heat quickly, but it also means they can heat up quickly if they find a warm spot. Some are surviving near the fires, in the narrow zones where the temperature is above freezing, but not hot enough to burn. They huddle in rock crevices, in the lee of boulders, anywhere that provides slight protection from the cold. A small troodon, one of the most intelligent dinosaurs, has found shelter in a cave system heated by geothermal activity. The rocks are warm to the touch, radiating heat from deep within the earth. The troodon is not alone here. Several other small dinosaurs in a family of mammals have found the same refuge. In the world before, they would have competed for this space, would have established territories, would have fought or displayed or negotiated. Now they simply coexist, huddled together in the darkness, enemies made irrelevant by mutual desperation. But these warm refuges are rare and scattered. For every animal that finds one, thousands die in the cold. The dinosaurs, after 165 million years of dominance, are being eliminated by simple thermodynamics. Their bodies, their metabolisms, Their entire biology is adapted to a warm world. That world no longer exists. 15 hours after impact, the temperature in mid-latitudes has dropped to -10 degrees Celsius. Water is freezing solid. The acid rain has stopped, not because the sulfur is gone from the atmosphere, but because it is too cold for rain. Instead, sulfuric acid is condensing as a fine mist that coats everything in a corrosive layer of ice. The small mammals are faring better than the dinosaurs. Their fur provides insulation. Their higher metabolic rate generates more internal heat. Their ability to seek shelter in burrows and caves protects them from the worst of the cold. But they are still suffering. Food is becoming critically scarce. The insects they normally eat are dying in the cold. The plants that produced seeds are dead. The small animals they sometimes scavenged are harder to find. A group of small mammals resembling modern shrews has found a cache of stored food in an abandoned dinosaur nest. Before the impact, a small oviraptorosaur was incubating eggs here, sitting on a nest it had carefully constructed and provisioned with vegetation. The oviraptorosaur is dead now, frozen solid a few meters from its nest. The mammals dig through the frozen vegetation and find the eggs beneath. The eggs are frozen solid, but the mammals do not care. They gnaw through the shells with their sharp teeth and lick out the frozen contents. It is not ideal nutrition, but it is protein and fat, the exact nutrients they need to fuel their high metabolisms in the cold. They eat all 6 eggs, leaving nothing but shell fragments, then burrow into the nest material itself, using it as insulation against the cold. This is survival at its most basic. Find food, find warmth, endure. The mammals are not thinking about the future or mourning the past. They are simply existing from moment to moment, driven by instinct and desperation to stay alive long enough to see another day. In the oceans, the cold is having different effects. The surface water is cooling rapidly, its temperature dropping toward freezing. This should cause the water to sink, driving circulation and mixing. But the normal patterns are disrupted. The influx of fresh water from vaporized ocean has changed salinity patterns. In some areas, a layer of less dense fresh water sits on top of the denser salt water, preventing mixing. This stratification is creating zones where the surface freezes while water just meters below remains liquid. A group of sharks has found itself trapped beneath a thin layer of ice. The sharks patrol the boundary between ice and water, confused and stressed. They can sense the open ocean beyond the ice, but they cannot reach it. They swim in circles, their movements becoming more frantic as oxygen levels drop and the ice thickens from above. Sharks, despite being fish, need a constant flow of water over their gills to breathe. Some species can pump water over their gills while stationary, but many cannot. These must swim continuously or die. The trapped sharks swim until exhaustion overtakes them, until their muscles can no longer function in the cold water, until they sink to the bottom and die. But not all sharks are trapped. In the deeper water, below the ice and the cold surface layer, some species continue to survive. They are hunting in darkness, as they have always done, using senses that do not require light. The abundance of dead and dying prey makes hunting easy. These sharks will survive the extinction event almost unchanged, as their ancestors survived previous catastrophes. 16 hours after impact, the first permanent ice is forming at high latitudes. This ice will not melt when the darkness eventually lifts. It marks the beginning of polar ice caps, features that will define Earth's climate for millions of years to come. Before the impact, Earth had no permanent ice anywhere on its surface. The planet was warm from pole to pole, covered in forests and swamps and shallow seas. That world is gone. In Antarctica, which just yesterday was a temperate forest inhabited by dinosaurs and small mammals, snow is falling and accumulating. The temperature has dropped to -20 degrees Celsius and is still falling. The trees, already stressed and dying from lack of light, are now freezing solid. The water in their cells expands as it turns to ice, rupturing cell walls, destroying tissue. The trees are dying from the inside out. Beneath the dying forest, small mammals are digging deeper into the soil, seeking the geothermal warmth that exists below the frost line. The permafrost is advancing downward at a rate of centimeters per hour, and they are digging frantically to stay ahead of it. Some succeed, reaching depths where the ground remains above freezing. Others do not, and they freeze in their burrows, their bodies preserved for millions of years. On the surface, the last polar dinosaurs are dying. These were species adapted to the long, dark winters of high latitudes, species that could survive months without sunlight during the polar night. But they were adapted to a world with warm summers and mild winters. They are not adapted to permanent darkness and permanent cold. They freeze like their tropical cousins, their bodies testament to the fact that adaptation has limits, that evolution cannot prepare life for catastrophes beyond all previous experience. 16 hours after impact, perhaps 80% of all species on Earth are extinct. The survivors are concentrated in a few environments: deep ocean vents, geothermally heated caves, tropical regions near the fires, deep burrows, and a few isolated pockets where conditions happen to be less severe. These survivors represent a tiny fraction of the biodiversity that existed 16 hours ago. But they represent all the biodiversity that will exist in the future. Every species alive today, every mammal and bird and fish and insect, is descended from the creatures surviving this night. The genetic bottleneck is extreme. Entire branches of the evolutionary tree are being pruned away, leaving only the smallest twigs to grow into the future. The cold is relentless, and it is global. There is no refuge in migration because every latitude is affected. There is no refuge in the ocean because the surface is freezing and the depths are anoxic. There is no refuge in the air because the atmosphere is toxic and the cold is killing anything that flies. The only refuge is in being small enough to hide, generalized enough to adapt, and lucky enough to be in the right place when the world ended. The long night is falling across Earth. It will last for months. When it finally ends, when the debris settles and the sun returns, the world will be unrecognizable. The age of dinosaurs is over. The age of mammals has not yet begun. This is the between time, the time of death and endings, the darkest hour before an uncertain dawn. But in the darkness, in the cold, in the ruins of everything that was, life persists, not thriving, not comfortable, but persisting. And persistence in this moment is everything. The temperature collapses, hours 16 to 20. 17 hours after impact, the planet has entered a thermal freefall unlike anything in Earth's recent geological history. Without sunlight to warm the surface, without the greenhouse effect of water vapor that has condensed and fallen as toxic rain, the planet is radiating heat into space with nothing to replace it. The global average temperature, which was 25 degrees Celsius before impact, has now dropped to -5 degrees, and it is still falling. The fires, which provided some warmth for the first half-day after impact, are beginning to die out. Not because they have run out of fuel, but because the cold is becoming so intense that combustion itself is affected. Fire needs oxygen, heat, and fuel. The oxygen concentration in the atmosphere is dropping as fires consume it, and photosynthesis has stopped. The temperature is so low that even burning material is struggling to maintain combustion temperature. One by one, the great continental conflagrations are sputtering out. In what will one day be Western North America, the last major fire is dying. The flames, which reached heights of 50 meters just hours ago, are now barely 2 meters high. The wood they are consuming is frozen on the outside, requiring ever more energy to heat to combustion temperature. The fire makes a last, desperate surge, consuming the remaining fuel in a final burst of heat and light, then collapses into smoldering embers. Within an hour, even the embers are cold. Darkness and cold reclaim the land. A small group of mammals had been surviving near this fire, using its warmth to stay alive. They huddled as close as they dared, balancing between burning and freezing, existing in the narrow zone where temperature was survivable. When the fire dies, they are faced with an impossible situation. The ambient temperature is -15 degrees Celsius. Their small bodies cannot maintain internal temperature in these conditions, not for long. They have one option: find another heat source or die. The mammals begin to move, guided by instinct, heading downslope where geothermal heat is more likely to exist. They travel in a tight group, pressed together, sharing what little body heat they can generate. The journey is only 2 kilometers, but in the darkness and the cold, it might as well be 200. They cannot see where they are going. They stumble over rocks, through ash drifts, across frozen ground that burns their feet with cold as surely as the fire burned them with heat. 3 of the 7 mammals do not survive the journey. They simply stop moving, their bodies unable to generate enough heat to keep their muscles functioning. They freeze in place, small lumps in the snow that has begun to fall. The remaining 4 press on, driven by a survival instinct that will not let them quit, even when death would be easier. They find a crack in the bedrock, a crevice that exhales warm, sulfurous air from deep within the earth. The warmth is salvation. They crawl into the crevice, down into the darkness, away from the frozen surface. The air temperature here is above freezing, perhaps 5 degrees Celsius. It smells terrible, thick with volcanic gases that would be toxic in higher concentrations. But it is warm. The mammals huddle together in this narrow space and sleep, exhausted beyond measure, but alive. 18 hours after impact, the phenomenon of impact winter is in full effect. The term is inadequate to describe what is happening. Winter implies a season that will end, a temporary cold that will give way to warmth. This is not a season. This is a climate shift that will persist for years. The debris in the atmosphere will take months to settle. Even when it does, the sulfur aerosols will remain, reflecting sunlight back into space, keeping the planet cold for years after the darkness lifts. The ocean's surface is freezing at an unprecedented rate. Sea ice is forming at latitudes where ice has not existed for 100 million years. The ice spreads from the poles toward the equator, covering the ocean in a white sheet that will eventually extend to within 30 degrees of the equator. This ice formation has a feedback effect. The white surface reflects what little sunlight penetrates the debris cloud, causing even more cooling. Marine life beneath the ice faces new challenges. Many species evolved in a world where ocean temperatures were relatively stable and warm. They have narrow temperature tolerances, unable to adapt quickly to the rapid cooling. Fish species that prefer warm water are swimming desperately toward the equator, toward the last pockets of ice-free ocean. But they are running out of space. The habitable zone is shrinking daily. A school of ancient fish, primitive relatives of modern bony fish, finds itself trapped between advancing ice to the north and south and anoxic water to the east and west. They swim in confused circles, seeking an escape that does not exist. The water temperature drops below their survival threshold. Their movements become sluggish. Their metabolisms shut down. They sink to the bottom and die, joining the billions of others in the growing layer of death on the seafloor. But some fish are adapting with remarkable speed. A population of small fish, in what will one day be the Arctic Ocean, has always lived at the edge of survivable temperatures. They possess antifreeze proteins in their blood, compounds that prevent ice crystals from forming in their tissues. This adaptation, which was marginally useful before, is now the difference between life and death. These fish survive as the water around them drops to -2 degrees Celsius. They will be among the founders of cold water fish lineages that dominate future oceans. 19 hours after impact, the temperature in mid-latitudes has reached -20 degrees Celsius. This is cold enough to freeze carbon dioxide. In some regions, particularly at high altitudes and latitudes, dry ice is forming alongside water ice. The atmosphere itself is beginning to precipitate out of the air. This is a phenomenon that should not be possible on Earth, that has not occurred since the planet was young and cold. But it is happening now. On the highest mountains, in the thin air where temperature drops fastest, carbon dioxide snow is falling. It looks like normal snow, but sublimates directly from solid to gas when touched, leaving no puddle, no trace except a puff of cold vapor. Animals that venture into these regions die within minutes, their lungs damaged by breathing air so cold it burns. A small feathered dinosaur, one of the last of its kind, has climbed a mountain seeking escape from predators that no longer exist. It dies at an altitude of 3,000 meters, frozen so quickly that its last breath is preserved as ice crystals in its lungs. Its body will remain here, freeze-dried and perfectly preserved until millions of years in the future, when erosion exposes it and scientists marvel at the quality of preservation. 20 hours after impact, 90% of all large land animals are dead. The definition of large has shifted dramatically. Now it means anything over 10 kilograms. The only large animals surviving are those with access to geothermal heat sources or those fortunate enough to be in the last warm zones near the equator, where dying fires still provide some warmth. A lone Ankylosaurus, a juvenile weighing perhaps 800 kilograms, has survived by sheltering in a volcanic cave system. The cave is heated by magma chambers far below, maintaining a temperature of 15 degrees Celsius, even as the outside world freezes. The Ankylosaurus shares this space with dozens of other animals, small mammals, lizards, insects, even a few other small dinosaurs. They are packed together in the warm darkness, former predators and prey reduced to desperate refugees. Food is scarce in the cave. There is no vegetation, no insects to speak of, just the occasional small animal that dies and is immediately consumed by the others. The Ankylosaurus is starving, its massive body requiring thousands of calories per day that are simply not available. It is losing weight rapidly, burning through fat reserves, beginning to metabolize its own muscle. It will not survive more than another week, even in this warm refuge. But for now, it is alive, one of perhaps a few dozen large dinosaurs remaining on the entire planet. The small mammals in the cave are doing better. They need less food, can survive on scraps and insects, and even fungus growing on the cave walls. They are reproducing too, their short generation times allowing them to adapt and evolve in real time. A female gives birth to a litter of 6, adding to the population of survivors. These offspring will never know the world their parents knew. They will be born into darkness and cold, and those conditions will be normal for them. 20 hours after impact, the atmosphere itself is changing in fundamental ways. The massive injection of carbon dioxide from burning forests should be causing global warming, but the effect is being overwhelmed by the cooling from debris and sulfur aerosols. However, this carbon dioxide is not going away. It is accumulating in the atmosphere, building up to concentrations not seen in millions of years. When the cooling finally ends, when the debris settles and the sulfur rains out, this carbon dioxide will cause rapid and extreme warming. The planet will swing from icehouse to greenhouse in a matter of decades. But that is in the future. Now, in the present, the cold is absolute. Water is frozen. Carbon dioxide is freezing. The air itself feels solid, thick with particulates and ice crystals. Breathing is difficult, each breath burning lungs with cold and acidity. The survivors breathe shallowly, conserving heat, conserving energy, conserving life itself. In the deep ocean, in the trenches and abyssal plains, the cold is even reaching here. The thermohaline circulation has slowed to almost nothing. The deep water, normally refreshed by sinking currents from the poles, is becoming stagnant. Oxygen levels are dropping. Temperature is slowly declining even at depths of 4,000 meters. The deep-sea communities around hydrothermal vents, which seemed isolated from surface catastrophe, are beginning to feel the effects. A deep-sea fish, blind and adapted to eternal darkness and cold, finds the water around its vent cooling as the circulation fails. The vent itself still flows hot and chemical-rich, but the surrounding water is changing. The fish can sense the change, but cannot understand it. It stays near the vent, in the narrow zone of warmth, its world shrinking to a few cubic meters of survivable space. 20 hours after impact, the survivors can be counted. Not as individuals, there are still millions of those, but as viable populations capable of recovering. Most species exist now in numbers too small for long-term survival. They are the walking dead, doomed by genetics and mathematics, even if they survive the immediate crisis. A population of 50 individuals is not enough to maintain genetic diversity. a population of 10 is guaranteed to go extinct within a few generations. Only species with large surviving populations, widely distributed across multiple refuges, have real chances of long-term survival. The small mammals, with their high reproductive rates and wide distribution, have thousands of surviving populations. The sharks, with their global range and ability to survive in many conditions, have dozens of viable populations. The small feathered dinosaurs, the ancestors of birds, have perhaps 20 or 30 populations scattered across the globe. The large dinosaurs, the icons of the Mesozoic, have 0 viable populations. There are individuals alive, perhaps a few hundred scattered across the planet, but they are not reproducing. They cannot find mates in the darkness. They cannot raise young in the cold. They cannot provide the massive amounts of food that large young require. They are evolutionary dead ends, the last of their kind, living fossils in a world that has moved on without them. The cold continues to deepen. 20 hours after impact, the planet is colder than it has been in 100 million years. And it will get colder still before it begins to warm. The survivors huddle in their refuges, in their caves and burrows and cracks in the earth, waiting for a change that will not come for months. The long night is not yet half over. The worst is still to come. But the survivors, the small and the hidden and the desperate, are proving that life is resilient beyond measure. They are enduring what should be unendurable. They are surviving what should be unsurvivable. And in their survival lies the seed of all future life on Earth. The last dinosaurs, hours 20 to 24. 21 hours after impact, the remaining large dinosaurs are facing their final hours. They are scattered across the planet in isolated pockets, individuals or small groups that somehow survived the initial catastrophe, the fires, the cold, the starvation. But survival has become a matter of mathematics, and the mathematics are unforgiving. Their bodies are too large, their metabolisms too demanding, their adaptations too specialized for a world that no longer exists. In a geothermal valley in what will one day be Wyoming, a small group of hadrosaurs has found temporary refuge. The valley is heated by hot springs and geysers, volcanic activity that keeps the air temperature above freezing even as the world outside freezes solid. Steam rises from pools of near-boiling water, creating a microclimate that is almost habitable. Almost. There are 5 hadrosaurs here, 3 adults and 2 juveniles. They are the last survivors of a herd that once numbered over 200. They stand in the shallow water at the edge of a hot spring, the warmth radiating up through their legs, barely enough to keep their core temperature from dropping to lethal levels. They are starving. The vegetation that surrounded the hot springs is dead, burned first by the thermal pulse and then frozen by the cold. There is nothing to eat. The hadrosaurs have been eating bark, lichens, even trying to digest the primitive algae growing in the hot springs. None of it provides adequate nutrition. They are losing weight rapidly, their bodies consuming muscle and organ tissue to stay alive. The juveniles are suffering most. Young animals have higher metabolic demands and smaller energy reserves. They need to eat more, not less, but there is nothing to give them. 22 hours after impact, one of the juvenile hadrosaurs dies. It simply lies down in the warm water and does not get up. Its mother stands over it for several hours, nudging the body, calling to it with soft vocalizations, but the juvenile is beyond response. Its heart has stopped, its body temperature has dropped, its brain has ceased all electrical activity. it is dead. The other hadrosaurs do not eat the body. They are herbivores, their entire digestive system optimized for breaking down plant cellulose. They cannot digest meat, even if instinct allowed them to try. The body floats in the hot spring, slowly cooking in the water, beginning to decompose. The smell is terrible, but the hadrosaurs cannot leave. Outside the valley, the temperature is minus 30 degrees Celsius. To leave is to die within minutes. Across the planet, similar scenes are playing out. The last Triceratops dies alone in a cave, its massive body too large to maintain temperature even in the shelter. The last Ankylosaurus freezes solid while trying to reach a heat source it could smell but never found. The last Tyrannosaurus rex, the most famous predator in Earth's history, dies curled in a ball in a shallow depression, trying desperately to conserve heat it could not generate. These deaths are not dramatic. There are no final battles, no last stands against impossible odds. The dinosaurs die quietly, gradually, their bodies shutting down system by system as the cold overwhelms their biology. They die confused and frightened, unable to understand what has happened, unable to comprehend that their entire world has ended. But not all dinosaurs are dying. The small, feathered theropods, the ancestors of birds, are proving remarkably resilient. Their feathers provide insulation that scales cannot match. Their high metabolic rates, which would seem disadvantageous, allow them to generate internal heat more efficiently. Their small size means they can shelter in spaces too small for larger animals, can survive on food sources too meager for bigger bodies. A small vagavus, a duck-like bird from the late Cretaceous, huddles in a rock crevice with its mate and 3 chicks. They are cold, hungry, frightened, but they are alive. The parents take turns venturing out into the darkness, searching for food. They find insects frozen in the ash, dead fish in frozen ponds, seeds preserved in the ice. They bring these back to the chicks and feed them, one tiny morsel at a time. The chicks are growing despite the adversity. They are developing adult feathers, building body mass, preparing to survive independently. In the world before, they would have taken weeks to fledge. Now, driven by the crisis, their development is accelerated. Within days, they will be capable of flight, of dispersing to find their own refuges, of continuing their species. This is evolution in action, natural selection operating at maximum intensity. The individuals with slightly better insulation survive. The individuals with slightly more efficient metabolisms survive. The individuals with slightly more behavioral flexibility survive. These tiny advantages, which would be barely noticeable in normal times, are now the difference between extinction and survival. 23 hours after impact, the global temperature has stabilized at minus 15 degrees Celsius, but only because it cannot drop much further without the entire atmosphere freezing. The planet has reached an equilibrium point where heat loss to space equals heat retention from the molten core below. This is as cold as Earth will get during this crisis, which is both a relief and a horror. Relief because the temperature will not drop further. Horror because this is the new normal, and it will persist for months. In the geothermal valley, the adult hadrosaurs are dying. 2 have already collapsed and died in the past hour. The third, the mother who lost her juvenile earlier, is standing alone in the hot spring, swaying slightly, her eyes glazed. She is experiencing multiple organ failure, her kidneys shutting down from dehydration and malnutrition, her liver unable to process the toxins accumulating in her blood. Her brain function is deteriorating, consciousness fading in and out. She takes a few steps forward, stumbles, regains her balance. She lifts her head and calls out, a long, mournful sound that echoes across the valley. It is a contact call, the same vocalization hadrosaurs use to maintain herd cohesion, to locate separated members, to communicate across distances. She is calling for her herd, for the 200 individuals that used to surround her, protect her, share her life. No one answers. The herd is dead. Her species is dead or dying. She is one of perhaps a dozen hadrosaurs remaining alive on the entire planet, and none of them are within hearing distance. The call fades into the darkness, unanswered and unanswerable. She collapses into the water and does not rise again. Her death takes another hour, her body slowly shutting down, her heart beating slower and slower until it stops. She is the last of her kind in this valley. When she dies, this particular population, this genetic lineage that stretches back millions of years, ends forever. The last juvenile hadrosaur, now orphaned, stands over the bodies of its mother and siblings. It is perhaps 2 years old, not yet sexually mature, not yet capable of reproduction. Even if it survives, even if it finds another hadrosaur, it cannot continue the species. It is a genetic dead end, a final echo of a lineage about to go silent. 24 hours after impact, the first full day of the post-impact world is ending. Not that day and night have any meaning now. The sun is still invisible behind the debris cloud. The darkness is absolute, and will remain so for months. But by the arbitrary measure of Earth's rotation, 24 hours have passed since the asteroid struck. The planet is transformed beyond recognition. The warm, humid, dinosaur-dominated world of yesterday is gone. In its place is a frozen wasteland, dark and toxic and nearly lifeless. 85% of all species are extinct. Of the remaining 15%, many are doomed by small population sizes or loss of habitat or disruption of food chains. The effective extinction rate, accounting for species that are still alive but cannot recover, is closer to 90%. The dinosaurs, as a group, are finished. A few individuals linger, scattered across the globe, but they are living on borrowed time. The large species are already extinct, or will be within days. The medium-sized species will last perhaps weeks. Only the smallest species, those under 5 kilograms, have real chances of survival, and most of those will fail as well. But one lineage will survive. The small, feathered theropods, the maniraptors, the group that includes birds, will make it through the bottleneck. They will survive in small populations in isolated refuges, feeding on seeds and insects and carrion. They will huddle together for warmth, will adapt to the cold, will find ways to persist in the darkness. And when the light returns, when the temperature rises, when the world begins to recover, they will emerge and diversify. These survivors will give rise to modern birds, to 10,000 species that fill every niche from penguins in Antarctica to hummingbirds in the Amazon. They will be the living legacy of the dinosaurs, proof that the age of reptiles never truly ended, but merely transformed. The birds are dinosaurs, descended from theropods, carrying forward the genetic heritage of creatures that once ruled the Earth. 24 hours after impact, in a cave system in what will one day be Montana, a small, bird-like dinosaur sits on a nest of 3 eggs. The eggs are precious, irreplaceable, perhaps some of the last dinosaur eggs that will ever be laid. The parent is exhausted, starving, barely able to maintain the body heat needed to incubate the eggs. But it does not leave the nest. Instinct, millions of years old, keeps it in place. The parent will die within 2 days, its body unable to sustain both itself and the eggs. But before it dies, one of the eggs will hatch. A tiny chick will emerge, blind and helpless, into a world of darkness and cold. It should die immediately. By all logic, it cannot survive. But it will be brooded by its dying parent, will receive the last of its parent's warmth and energy, will be fed the last insects its parent can find, and somehow, impossibly, it will survive. It will grow feathers in the darkness. It will learn to find food by sound and smell. It will huddle with other survivors, sharing warmth, sharing the desperate instinct to live. And it will carry forward the dinosaur lineage into an uncertain future. 24 hours have passed since the asteroid struck. The first day in a new world. A world that will take millions of years to heal, that will never return to what it was, that will evolve in directions impossible to predict. The age of giants is over. The age of mammals has not yet begun. This is the between time, the extinction boundary, the moment when one world ends and another struggles to be born. In the darkness, in the cold, in the ruins of everything that was, life persists. Battered, diminished, reduced to the smallest and most desperate survivors, but persisting. And persistence, as it has always been, is enough. Because given time, given millions of years, persistence becomes recovery. Recovery becomes diversification. Diversification becomes the explosion of new life that will fill the emptied world. The dinosaurs are dying, but life itself is not dying. And from the ashes of the Cretaceous, from the survivors huddling in their refuges, will come the world we know. A world of mammals and birds, of flowering plants and insects, of diversity and abundance that rivals even the world that died today. But that is in the future. Now, at the end of the first day, there is only darkness and cold and the stubborn refusal of life to surrender. The worst is over, though the survivors do not know it. The temperature will not drop further. The toxic rain has stopped. The fires have burned out. What remains is endurance, the long, slow wait for conditions to improve, for the debris to settle, for the sun to return. The first 24 hours after impact have ended. The dying will continue for months, but the rate will slow. The survivors will begin to adapt, to find equilibrium with the new conditions. And somewhere, in the far future, scientists will study this day, will reconstruct what happened, will marvel at the catastrophe and at the resilience of life. They will find a layer of iridium in the rocks, evidence of the asteroid. They will find shocked quartz, proof of the impact. They will find a mass grave of fossils, all the species that died together, all preserved in a single moment of geological time. They will find the boundary between the Cretaceous and the Paleogene, the line between one world and another. And they will understand that 66 million years ago, hell came to Earth. And somehow, incredibly, life survived. Dawn after Doomsday, Hour 24, Epilogue. 24 hours and 1 minute after impact. The arbitrary marker of one full rotation of the Earth has passed, though no one alive can observe it. the sun remains hidden behind a debris cloud that now encircles the entire planet, a shroud of pulverized rock and sulfur compounds that will persist for months. The darkness is total. The cold is absolute. The world as it existed yesterday no longer exists in any meaningful sense. But something has changed, something subtle, something that no individual organism can perceive, but something real nonetheless. The planet has stabilized. The temperature has stopped dropping. The rate of extinction has slowed from catastrophic to merely devastating. The worst is over, though the crisis will continue for months, even years. Earth has survived the initial impact. What remains is the long, slow process of recovery. In the geothermal valley where the last hadrosaurs died, the hot springs continue to flow. Steam rises into the frozen air, creating columns of fog that glow faintly orange from the reflected light of volcanic vents deep below. The water temperature is 90 degrees Celsius, the air temperature minus 20 degrees. The gradient between them creates a narrow zone, perhaps 5 meters wide, where the temperature is survivable. A small mammal emerges from a burrow at the edge of this zone. It is a marsupial, roughly the size of a modern opossum, with fur thick enough to provide insulation against the cold. It moves cautiously, testing the air with its sensitive nose, listening for sounds of danger in the darkness. But there are no predators anymore. The tyrannosaurs are dead. The raptors are gone. The skies that once held pterosaurs are empty. This small mammal, which spent its entire evolutionary history hiding from predators, is now free to move openly. It approaches one of the dead hadrosaurs, the juvenile that died 23 hours ago. The body has been partially cooked by the hot spring water, partially frozen by the air. The mammal sniffs carefully, then begins to feed. The meat is tough and strange tasting, nothing like the insects and small animals it normally eats, but it is protein and fat, and the mammal's body desperately needs both. It eats for several minutes, consuming as much as its stomach can hold, then retreats to its burrow. This scene, this small mammal feeding on a dead dinosaur, is symbolic in ways that will only be understood millions of years in the future. This is the changing of the guard, the transition from one age to another. The mammals, which have lived in the shadow of dinosaurs for 165 million years, are inheriting the Earth. Not through conquest or competition, but through survival. They are the ones still alive when the music stops. 25 hours after impact, in the darkness beneath the debris cloud, the first hints of atmospheric clearing are beginning. Not at the surface, where the air remains thick with ash and sulfur, but in the upper atmosphere. The largest particles, the house-sized boulders and car-sized rocks ejected by the impact, have already fallen back to Earth. What remains aloft are smaller particles, dust, ash, sulfur droplets. These will take months to settle, but they are settling, grain by microscopic grain. High above the frozen surface, at an altitude of 30 kilometers, in the stratosphere where the air is thin and cold, a new phenomenon is beginning. The sulfur compounds in the air are reacting with what little water vapor remains, forming tiny droplets of sulfuric acid. These droplets are so small that they can remain suspended in the air for years, scattering sunlight, creating a persistent haze that will cool the planet long after the dust settles. But even this will eventually end. The sulfur will rain out. The dust will settle. The sun will return, first as a dim glow, then as a pale disk, finally as the blazing star that has warmed Earth for 4.5 billion years. When that happens, the survivors will emerge from their refuges and begin the slow process of reclaiming a world. 26 hours after impact, the ocean is a graveyard stretching from pole to pole. The surface is covered with a thick mat of dead plankton, dead fish, dead everything. This organic matter is beginning to sink, drifting down through the water column in an endless rain of death. The seafloor is being buried under a layer of organic-rich sediment that will eventually become a distinct geological marker, a black shale rich in carbon and iridium, visible in rock cores taken 66 million years in the future. But beneath this layer of death, life persists. On the seafloor, in the deep trenches, around hydrothermal vents that continue to flow regardless of surface catastrophe, ecosystems are surviving almost unchanged. A tube worm colony, existing in total darkness at a depth of 3,000 meters, is unaware that the surface world has ended. The worms filter chemicals from the vent water. The bacteria in their tissues metabolize sulfur. The cycle of life continues as it has for millions of years. These deep-sea communities will be the seeds of oceanic recovery. When the surface ecosystems collapse completely, when the last of the marine reptiles dies, when the ammonites are extinct, these vent communities will persist. And eventually, organisms from these communities will migrate upward, will colonize the empty ocean, will diversify into new forms adapted to a new world. 27 hours after impact, in a cave system heated by geothermal activity, a population of small mammals is thriving in ways that would have been impossible yesterday. There are perhaps 200 individuals in this cave network, representing a dozen different species. They are packed into chambers and tunnels, living in densities that would trigger aggression and territorial behavior under normal circumstances. But these are not normal circumstances. The mammals have formed an unintentional community, united by their common need for warmth and shelter. Predators and prey coexist, not through choice, but through necessity. A small carnivorous mammal, which would normally hunt the herbivorous species around it, is too weak from hunger to attempt predation. It survives on insects and scraps, on whatever it can scavenge without expending the energy to hunt. This forced coexistence will have long-term evolutionary consequences. The mammals in this cave will interbreed more readily than isolated populations, will share genetic material across species boundaries in rare cases, will exchange parasites and diseases that will shape their immune systems. When they eventually emerge and disperse, they will carry these influences with them, spreading adaptations across the mammalian lineage. 28 hours after impact, the first signs of biological recovery are appearing, though they are invisible to any observer. In the soil, beneath the layer of frozen ash, bacteria are still active. Decomposers are breaking down dead organic matter, recycling nutrients, maintaining the chemical cycles that underpin all life. Fungal networks, vast underground webs of mycelium, are damaged but not destroyed. They are dormant now, waiting for conditions to improve, but they are alive. These decomposers and these fungi will be critical to recovery. When plants eventually return, they will need soil with nutrients. But the fires have burned away most organic matter. The acid rain has leached away minerals. The ash has buried everything. The soil is effectively dead, sterile. It will take the bacteria and fungi years to rebuild soil fertility, to create conditions where plants can grow again. But they will do it. Life is patient. Evolution operates on timescales that make human history look like an eye blink. What seems impossible now, the recovery of a planet, will be routine on geological timescales. Earth has suffered worse extinctions than this. The Permian extinction, 250 million years ago, killed 95% of all species. Earth recovered from that. It will recover from this. 30 hours after impact, in scattered locations across the globe, the survivors are beginning to establish patterns that will define the post-impact world. The mammals are primarily nocturnal, which gives them an advantage in a world of permanent darkness. They are omnivorous, able to eat whatever they find. They are social, forming groups that can share warmth and information. These traits, which evolved in the shadow of dinosaurs, are now the traits that ensure survival. The birds, descended from small feathered dinosaurs, are surviving through different strategies. They can fly, which allows them to cover large distances in search of food and refuges. They can eat seeds, which remain viable even when frozen. They have excellent vision, or did in the world before. And though vision is useless in this darkness, the brain structures that processed visual information can be repurposed for processing sound and spatial memory. A small bird, perhaps one of the last of its species, has found a geothermal vent in what will one day be Iceland. The vent is surrounded by a thin layer of unfrozen ground, perhaps 20 meters in diameter, the only ice-free soil for thousands of kilometers in any direction. Primitive mosses and lichens are growing here, kept alive by the warmth and moisture from the vent. The bird feeds on insects that are feeding on the mosses, a tiny food chain sustained by geothermal heat in the midst of a frozen wasteland. This bird will survive. It will find a mate, another refugee drawn to the warmth of the vent. They will breed, will raise chicks, will establish a population. Their descendants will eventually disperse across the recovering world, will evolve into dozens of new species, will fill niches left empty by extinction. This single bird, this individual survivor, is an ancestor to millions of future birds. 48 hours after impact, 2 full days since the asteroid struck, the death toll has stabilized. Approximately 85% of all species are extinct. Of the remaining 15%, perhaps half are functionally extinct, existing in populations too small to recover. The effective extinction rate is around 90%, comparable to the worst mass extinctions in Earth's history. The large dinosaurs are gone, all of them. Every species over 100 kilograms is extinct. The tyrannosaurs, the sauropods, the ceratopsians, the ankylosaurs, all extinct. The medium-sized dinosaurs, those between 10 and 100 kilograms, are nearly extinct. A few individuals linger in geothermal refuges, but they are doomed. They will die within weeks from starvation or cold or simple loneliness, unable to find mates, unable to reproduce. Only the smallest dinosaurs, those under 5 kilograms, have viable surviving populations. And most of these are bird-like theropods, the maniraptors, the group that will give rise to modern birds. These survivors number perhaps 10,000 individuals scattered across the globe. From this tiny bottleneck, from these desperate refugees, will come all future birds, eagles and hummingbirds, penguins and parrots, ostriches and owls. The marine reptiles are extinct. The mosasaurs, the plesiosaurs, the sea turtles of the Cretaceous, all gone. The ammonites, which survived 350 million years of Earth history, are extinct. The reef-building corals are extinct. The specialized filter-feeding fish are extinct. The ocean has lost 75% of its biodiversity, and the remaining species exist in populations struggling to find food in a dying sea. But some groups have been spared. The sharks have suffered losses, but many species survived. The bony fish, the teleosts, have taken heavy casualties but remain diverse. The deep-sea organisms around hydrothermal vents are almost untouched. The marine snails and clams, while reduced in numbers, have enough survivors to eventually recover. The ocean is devastated, but it is not dead. 1 week after impact, the debris cloud is beginning to show the first signs of settling. At the surface, visibility has improved, from 0 to perhaps 10 meters in some areas. It is not much, barely enough to distinguish shapes in the darkness, but it is improvement. The temperature remains below freezing across most of the planet, but it has stabilized. The acid rain has mostly stopped, the sulfur having precipitated out of the lower atmosphere. The survivors are adapting to the new conditions. Mammals are emerging from their burrows for longer periods, learning to navigate in near-total darkness, finding food sources that did not exist before the impact. They are eating things their species never ate before: fungi, lichens, carrion, even each other when desperation demands it. Evolution is operating at maximum intensity, selecting for flexibility, for intelligence, for the ability to learn and adapt. 1 month after impact, perhaps 5% of the original biodiversity remains alive. This represents the hardcore survivors, the species that not only survived the initial catastrophe, but are actually reproducing, establishing populations, beginning the slow process of recovery. These are the founders of the future, the ancestral species from which all future diversity will arise. The debris cloud has thinned considerably. During the day, if one can call it day, there is now a faint glow in the sky, a dim illumination that suggests the sun still exists beyond the veil. It is not enough for photosynthesis, not enough for plants to grow, but it is a promise. The darkness will not last forever. The temperature is still below freezing across much of the planet, but localized warming is occurring near the equator and in geothermally active regions. Ice is melting in some areas, creating small pools of liquid water where life can persist. Plants, or rather their seeds and spores, are beginning to germinate in these warm pockets. They are not the same plants that existed before. Those species are mostly extinct. These are opportunistic species, weeds and pioneers, plants that can grow quickly in disturbed soil, that can tolerate extreme conditions. 3 months after impact, the world is still dark and cold, but the trend is toward recovery. The debris cloud has thinned enough that perhaps 1% of normal sunlight reaches the surface. This is enough for some photosynthesis to occur. Hardy plants, lichens, and mosses, and primitive ferns are beginning to grow in favored locations. The first green shoots are appearing in the ash-covered wasteland, tiny beacons of hope in a gray world. The survivors are dispersing from their refuges, exploring the transformed landscape, establishing territories in the ruins. The mammals, now freed from predation pressure, are diversifying rapidly. Species that were rare before the impact are thriving. Species that were common are extinct. The evolutionary dice have been rolled again, and they have come up showing different numbers. Birds are spreading across the continents, their ability to fly giving them access to resources that ground-dwelling animals cannot reach. They are finding seeds in the ash, insects emerging from dormancy, small animals to prey upon. They are singing again, filling the silence with calls and songs, re-establishing the soundscape of life. 6 months after impact, the sun is visible as a pale disk in the sky. The debris has mostly settled, leaving only the sulfur aerosols in the stratosphere to scatter light and maintain below normal temperatures. But even these are beginning to rain out, to be washed from the atmosphere by the resumption of the water cycle. The planet is still cold, still damaged, still far from normal, but it is healing. Photosynthesis is occurring at perhaps 10% of pre-impact levels. This is enough to support plant growth, to begin rebuilding the primary productivity that underpins all food chains. Ferns are spreading across the continents, their spores dispersing on the wind, their fronds unfurling in the dim sunlight. These are not the same ferns that existed before. Many species are extinct, but ferns as a group, as a strategy for survival, have proven remarkably resilient. The ocean is recovering more slowly. The surface waters remain depleted of oxygen and nutrients. The food chains are broken. But in coastal areas, in shallow seas where runoff from the land brings nutrients, algae are beginning to bloom. These algae are not the same species that existed before, but they are performing the same function, converting sunlight and nutrients into biomass, creating the foundation of marine food webs. 1 year after impact, the planet is recognizable again as a living world, though vastly changed from what it was. The global average temperature has risen to near freezing, cold compared to the pre-impact greenhouse world, but warm enough for liquid water to exist across most of the planet. The ice caps that formed during impact winter are beginning to melt, though they will not disappear entirely. Earth now has permanent polar ice for the first time in over 100 million years. The debris cloud is gone. The sulfur aerosols have mostly washed out. The sun shines clearly for the first time in a year, and the survivors look up at a sky they have never seen. For the young born after the impact, this is their first glimpse of blue sky, of sunlight unfiltered by ash and smoke. It is blinding, overwhelming, beautiful beyond description. Plants are spreading rapidly now, covering the ash-covered ground in a carpet of green. But the composition of vegetation has changed dramatically. The flowering plants, the angiosperms, which were dominant before the impact, have been hit hard. Many species are extinct. What survives are the generalists, the weeds, the pioneering species that can grow quickly in disturbed soil. Ferns are everywhere, covering vast areas with their simple fronds. This fern spike will be visible in the geological record 66 million years in the future. A layer of fern spores marking the recovery from extinction, showing that ferns were the first plants to recolonize the devastated world. Behind the ferns come the survivors of other plant groups: conifers, palms, a few species of flowering plants that made it through the bottleneck. The mammals are thriving, diversifying, filling niches left empty by the extinction of dinosaurs. They are still small, most under 10 kilograms, but they are no longer limited by predation pressure from large carnivorous dinosaurs. They can emerge during the day, can grow larger, can experiment with new diets and new lifestyles. The age of mammals is beginning. 10 years after impact, the ecosystems have stabilized into a new equilibrium. The extinction event is over. The species that are going to survive have survived. The species that were doomed have died. What remains is approximately 10% of the biodiversity that existed before impact. But this 10% is reproducing, expanding, evolving. The large dinosaurs are extinct. This is final, permanent, irreversible. Never again will 40-ton sauropods browse the treetops. Never again will Tyrannosaurus rex hunt across the plains. The age of giant reptiles is over. Ended not by competition or climate change, but by a random asteroid strike, a cosmic accident, a piece of bad luck on a planetary scale. But the dinosaurs as a group are not extinct. The birds are dinosaurs, theropods, direct descendants of the small feathered predators that survived the impact. They carry forward the dinosaur lineage into the future, and they are diversifying rapidly, evolving into ecological roles their ancestors never filled. There are birds becoming flightless and growing large again, recreating in miniature the size range of extinct dinosaurs. There are birds becoming specialized predators, hunters, scavengers. The dinosaurs have not died, they have transformed. 1 million years after impact, Earth is a different planet. The impact crater in what will be called the Yucatan is still visible, a depression 150 kilometers across, slowly being filled by sediment and vegetation. The layer of iridium-rich debris that circles the globe is buried now, covered by a meter of new sediment, invisible to surface observation, but permanent in the geological record. The climate has stabilized at levels cooler than before the impact. The permanent polar ice caps are regulating global temperature, creating more pronounced seasons, driving ocean circulation in new patterns. This cooler climate will persist, with variations, for millions of years. The hothouse world of the Cretaceous is gone, replaced by a more temperate, more variable climate. The mammals have diversified into hundreds of new species. They are filling niches left empty by dinosaurs. Large herbivores, small herbivores, carnivores, omnivores, insectivores. They are experimenting with new body plans, new diets, new behaviors. Some are returning to the ocean, their limbs transforming into flippers, their bodies streamlining for aquatic life. These will eventually become whales and dolphins, mammals that return to the sea their ancestors left hundreds of millions of years ago. The birds have diversified even more dramatically. There are large, flightless birds filling the role of medium-sized herbivores. There are small insectivorous birds filling every forest niche. There are predatory birds hunting mammals and other birds. There are water birds fishing in lakes and oceans. The birds have proven that the dinosaur body plan, refined over 165 million years, is still viable, still successful, still capable of dominating ecosystems. 66 million years after impact, in the far future, a species of intelligent primate is excavating rocks in a desert that was once a shallow sea. They are paleontologists, scientists dedicated to understanding the history of life on Earth. They find a layer of rock different from the layers above and below it. It is rich in iridium, an element rare on Earth, but common in asteroids. It contains shocked quartz, minerals that can only form under the intense pressures of an impact. They find fossils below this layer, dinosaurs, ammonites, marine reptiles, all the diversity of the Cretaceous world. They find different fossils above this layer, mammals, birds, flowering plants, the ancestors of the modern world. The transition is abrupt, geologically instantaneous, representing a change that occurred in hours, not millions of years. The scientists reconstruct what happened. They find the crater in the Yucatan. They calculate the size of the asteroid, the energy of the impact, the global consequences. They understand that 66 million years ago, an asteroid struck Earth and changed the course of evolution forever. They understand that without that impact, without that cosmic accident, the mammals might never have risen to dominance. Intelligence might never have evolved. They themselves might never have existed. They are looking at their own origin story, written in rock and fossils, preserved for 66 million years. They are the descendants of the survivors, of the small mammals that hid in burrows, of the small birds that sheltered in caves, of the creatures that endured when the world ended. Every human being, every mammal, every bird is descended from the survivors of the worst day in the history of complex life on Earth. The scientists understand something else, too. They understand that extinction events are not aberrations. They are part of how evolution works, how diversity is created and destroyed and recreated. They understand that Earth has suffered worse catastrophes than the asteroid impact and has always recovered, has always generated new diversity from the survivors. They understand that they are living in a window of time, a period of unusual stability between mass extinctions. The last major extinction was 66 million years ago. The next one is coming, though when and how remains unknown. It might be another asteroid. It might be massive volcanism. It might be climate change. It might be something they themselves cause, a sixth mass extinction driven by their own actions. But they also understand that life itself is resilient beyond measure. Individual species go extinct. Entire ecosystems collapse. But life persists. Life adapts. Life recovers. It took Earth 10 million years to fully recover from the asteroid impact, to rebuild biodiversity to pre-impact levels. But it did recover. The planet healed. The survivors diversified. The world was made new. This is the lesson of the asteroid impact, the meaning extracted from catastrophe. Life is fragile in individuals, but robust in aggregate. Species are temporary. Evolution is permanent. The world that exists today is built on the ruins of worlds that came before, and the world of the future will be built on the ruins of today. 66 million years ago, hell came to Earth. An asteroid 12 kilometers across struck the Yucatan Peninsula with the force of 10 billion nuclear weapons. The impact created a crater 35 kilometers across. It vaporized trillions of tons of rock. It ignited global firestorms. It poisoned the atmosphere with sulfur. It plunged the planet into darkness and cold that lasted for months. 85% of all species went extinct. The dinosaurs, which had dominated the planet for 165 million years, were wiped out. The marine reptiles that ruled the oceans were gone. The pterosaurs that controlled the skies vanished. The ammonites, 350 million years old, went extinct. Entire ecosystems collapsed. The world ended. But life survived. In burrows and caves and cracks in the rocks, in deep ocean vents and geothermal springs, in rare pockets of livable conditions scattered across a dying planet, life persisted. The survivors were not the strongest or the largest or the most specialized. They were the small, the adaptable, the lucky. They endured when endurance seemed impossible. They survived when survival seemed hopeless. And from those survivors came everything that exists today. The mammals that inherited the land, the birds that filled the skies, the fish that repopulated the oceans, the plants that covered the scorched earth. The entire modern world, all its diversity, all its beauty, all its complexity, descended from the few who survived the worst day in Earth's history. This is the story of the first 24 hours after the asteroid impact. It is a story of death on an unimaginable scale, but it is also a story of survival against impossible odds. It is a story of endings, but also of beginnings. It is the story of how one world died and another was born. The dinosaurs died. Long live the dinosaurs.